Yes, yes, sure. Yeah.
Mm.
So how is it in Uppsala? Like, I mean, is it still lockdown or?
I mean, we have not had lockdown here at all.
I mean, but I mean, in general, I think.
But I mean, the situation is very bad.
Okay.
In fact, my father-in-law passed away just 10 days
Ooh.
ago.
Oh, this is sad. Oh,
Yeah, he got COVID, and yeah,
oh.
it's quite tough.
Mm.
But yeah, so
Here, I think is also this. I don't know. I mean, the numbers are reasonably in control. That's what people say, but it's still scary. I think here also. Like
it depends how you count also.
exactly, yeah. Okay. So yeah. Anyway, I'll also mention this in the opening remark, but I mean, my co-organizer Srivatsan has. I mean, he is a father now, so he got his son Amrit a
Oh,
few days back. Yeah.
wow! Congratulations.
Yeah. Congratulations to him.
Yeah.
Hello, Kumar.
Hi. So the talk is for 1 hour with 50 minutes plus 10 minutes for questions, or what is the plan, Prakash?
So, yeah, this is what we imagined, but you are the chair, so you can choose, I think.
Okay.
Yeah,
Parosh,
this is what we imagined, about 50
Oh.
minutes.
So Parosh, is 50 minutes plus 10 minutes for questions okay with you?
Yeah, I have not, I don't know how much time it takes. It can
Okay.
take 50 minutes, but I don't know.
No,
1
I'm sure
hour.
if you go a little bit ahead, that should be okay.
Yeah.
And also, I think
Yeah.
we'll allow people to
Yeah.
ask questions. Is it okay if I allow
Yeah.
people to unmute and ask questions during the talk?
Yes, but please make me aware of questions. I will not check the chat.
Not through the chat. No, not through the chat. I'm asking whether they can unmute and just ask you in the
Yeah,
meeting.
yeah.
That's okay.
Yeah.
That's probably easier. The
It's
chat,
fine.
I think, is difficult to read. I will
Yeah.
monitor the chat if there are questions on the chat, but
Yeah.
it
Yes.
may be better to just unmute because it's a small audience and I think it's easier.
Yeah, sure.
So how cold is it there now?
It's not cold at all. It's like 8-9 degrees.
Ah, okay.
But it's very dark. I have not seen the sun for, I don't know, 3-4 weeks because it's cloudy. I mean, we have high clouds, which are very thick. So, and the sun is weak. So you don't see it.
Is there snow on the ground yet? Not yet.
No, we will not have snow for some time now. I mean, last year we didn't have snow at all, which is amazing. It's good for my flowers. They survive much better. I will share my screen to see whether.
Sure.
So do you see it?
Yes, very well. Yeah.
And the cursor also?
Yes, I can see the cursor also. You can just leave it as it is. I don't think we need to change this. It can be as it is.
Yeah.
Perfect.
So maybe you can also try to move around your slides, because one of the talks at least had some problems when.
Okay. Prakash is saying try to move the slide to the next slide.
On the slides,
yeah.
Yeah.
Is it working well?
Yes, working fine. Yeah.
Yeah.
Yep.
I have just given a course online, so I'm used to it now. I had an undergraduate course on concurrent data structures.
Okay. So Parosh, your title is different from the title on Prakash's webpage. Okay, so I should use this one. Good, I'll use this.
I don't remember. It's a bit
it said stateless model checking and release across semantics.
It's the same thing.
It doesn't
matter. No.
I think we have 3 more minutes. Maybe we can.
I think it's fine. It's better to wait until people turn up.
Yeah, we should wait till the time.
Yeah.
So Prakash, the plan is that you will say something initially. Is it right?
Yes, and then I hand over control to you.
Yeah. And then I will introduce Parosh. Okay, very good. Thanks.
So if you wish, I can unshare until I start the screen. And then I share again later.
No, but it's okay. You could also keep it shared.
Okay.
It's up to you.
Good.
Kumar, you are on mute.
Okay.
Yeah, I was saying that keep the slide on. I would rather people see the slide than my face.
Okay.
So,
Yeah, so it's 1:30 in my watch, so maybe we can start. So welcome all of you to the Advances in Verification workshop. You might all be aware that this is organized as part of the FSTTCS conference. We thank Sunil Simon for providing us with the opportunity to organize this workshop. The workshop, as the name suggests, is aims at discussing or surveying recent advancements in the field of verification. So there will be two 2.5-hour sessions in this workshop, and each of these sessions will have 2 1-hour talks with half an hour gap in between them. The sessions by themselves will be separated by 1.5 hours of a break. We'll have Parosh and Carolina speaking in the first session, and Joshua and Yako in the second session. These talks will be broadcasted live on YouTube, and we have also set up some gather meeting point so that you can discuss and socialize there. So we'll go to the workshop, but before we go to the workshop, I have a very nice news to share with you. I mean, my co-organizer Srivatsan very recently became a father. His son Amrit was born a few days back. Yeah, so with this happy note, we start the workshop. Kumar, I hand over the control to you.
Hi, it's my pleasure to introduce the first speaker, Parosh, a good friend. Parosh Abdullah is at the University at Uppsala, and actually to this audience, he certainly needs no introduction. His work and this is well known. Parosh has made fundamental contributions to the verification of infinite state systems. In particular, his work on lossy channel systems and well-structured systems is some of the most influential works that you find in the area. He's made contributions to other areas such as verification of parameterized systems, time systems, and more recently to the verification of programs under various weak memory models, relaxed memory models, as well as to partial order verification. And today's talk I understand, involves some of these. He is a recipient of many awards, including the CAV Award and the LIX Test of Time Award. And without any further ado, I request Parosh to give the talk. And for the audience, if you have any questions, since it's a small audience, you could simply unmute yourself and ask the question. I mean, the chat is probably difficult for him to monitor. So I would prefer that you can just unmute yourself and ask the question, and I have checked with Parosh and he's fine with this. Okay, over to you, Parosh.
Okay, thank you very much for the invitation and for the nice introduction. So this is the title of the talk, which is a bit different from the one that was announced, but it's the same talk. So an outline of the presentation. So in fact, this will be a high-level description of a research area rather than a detailed description of technicalities. So I would like to convey a message, namely that we have to deal with memory models in the context of concurrency, and these pose new problems and new challenges. So I will try to give you a flavor of the new challenges that arise because we have to deal with memory models, and then give you a high-level description of some of the ideas we have and some of the solutions that we have provided in recent years. So first, I will talk about memory models in general, and then I recall, just to illustrate the concepts, I'll recall the classical, the well-known sequential consistency or SC semantics, and then I'll concentrate on one particular memory model, which is called the release-acquire memory model, and use it as an example to illustrate both the challenges and the types of problems we are trying to solve, and to motivate also why these models are interesting. And in particular, I will concentrate on verification, and then at the end of the talk, as an example of a verification framework, I will describe how to instantiate the framework of dynamic partial order reduction, or sometimes called stateless model checking, to deal with the release-acquire semantics. And then I will report on some experiments that we have conducted. So this type of research is both theory, where you develop semantics, for instance, and models for these memory models, algorithms, where you develop testing or verification algorithms, and also code implementation. So it's not only theory, it's a mixture of theory, algorithms, and coding. And then I give some conclusions and some directions for future work. So first, the semantics for the release acquire model that I will present in this paper is based on these two, in this presentation is based on these two papers that I mentioned here. And the results are a high-level description of several results that we have produced in the last 3, 4, or 5 years. And this is a list of my co-authors, for whom I am very grateful. So if you want to have more information about what I will be talking about in this presentation, you can, of course, ask me, but also there are published papers that contain the information. But no details here, only a high-level description of concepts and solutions. Okay, so first, memory models, and to start with sequential consistency. So in this presentation, we are in general interested in concurrent programs. And I will, to make things easy to understand, I will concentrate on one particular model of concurrent programs, namely processes that communicate through shared variables. So this means that you have a set of processes. In this particular example, you have two processes, P1 and P2, and they share two variables, X and Y. And this black box here is what we call the shared memory. So it's a function that defines the values, the current values of the shared variables. So in this particular case, both X and Y have values that are equal to 0 in the shared memory. And what these processes can do in this presentation is that they can perform read and write operations on these variables. And in SC, all these operations are atomic, as we will see. And this will not be the case in general for other memory models. So again, we have a set of processes. They share a set of variables on which they can perform reads and writes. Of course, in general, you may have other types of communication mechanisms. You may have message passing, you may have rendezvous, you may have broadcast, but all the concepts that I describe here can be extended to deal with these frameworks. But to keep things simple, I will use the shared variable model. And also, I only consider operations that are reads and writes. In reality, there are other operations that can be used, for instance, atomic operations like atomic read and writes, fences, locks, etc. So, but here today only reads and writes. So if you look inside the process, I will not give any formal models, no formal semantics. Such details can be found in the papers that I mentioned in the previous slides. But I will illustrate processes as simple pieces of code. So here, if you look at the definitions of P1 and P2, you see that you have some write and read instructions. In fact, by write instruction, I mean an instruction that writes a new value to a shared variable. And by a read instruction, I mean an instruction in which you read the value of a shared variable, X and Y in this case, and you may store them in some local variable, A and B in this case. So I have the program counter, which tells you the instruction, which is next to be executed inside the process, as usual. And we have, in addition to the shared variables, we have local variables that we use to store the values of the shared variables that we may read from the shared memory. Okay, so in fact, this example is in the context of memory models is usually referred to as the store buffering example. But this is nothing but a simplification or an abstraction of the well-known classical Decker's protocol for mutual exclusion. In fact, this is one of the basic protocols which we teach already in our first courses in undergraduate courses on operating systems, multi-process systems, etc. And the idea of this protocol is that you have two processes competing for a critical resource, and they cannot enter their critical sections at the same time. And the idea is that when a process starts to execute, it sets one shared variable x, in this case y in the case of P2, to 1. And if the second process tries to enter its critical section, it has first to read the shared variables which are set by the other process. And it cannot be the case that both tests will succeed. So here we have I model this as an assertion in this example, which says that, is it the case, can you execute these two processes, this concurrent program, and in the end obtain a configuration of the program in which this assertion holds, that A is equal to 0 and B is equal to 0. Where A is equal to 1 means that P1 is in its critical section, if you wish, if you know the Decker's protocol. If you don't know it, it's fine. Just think about this as a concurrent program consisting of two processes. And in the end, you would like to guarantee or to check whether you satisfy the assertion that both A and B are equal to 0. In this case, obviously, under the SC semantics, this will not be the case, because however you execute the program, one of these two processes will start. So if you say P1 starts, then X will be set to 1. And then when P2 eventually executes this instruction, it will get the value 1 in B. And therefore, this part of the conjunction will not be satisfied. And symmetrically for the other scenario where P2 starts. So you cannot reach a configuration in which both A is equal to 0 and B is equal to 0. So, and this is true if we interpret the program over the classical SC semantics. So SC semantics, in this particular instance, you have shared memory, shared variables. The processes perform read and write operations atomically, and this is important, which means that if you perform a write operation, then you update the memory immediately. You update the value of the variable in the shared memory immediately, atomically. And if you read the value of a shared variable, then you read directly from the memory. So all these operations are atomic, and their effects will be visible immediately in the whole system. Now, so this is one important characteristic of the SC semantics. You execute instructions of any given process in program order, one by one, as they are given in the code of the process. This is in general not the case, again, for other memory models. And then you interleave the instructions of different processes. And this is the source of non-determinism, which means that even if your processes are deterministic, which is the case in this presentation, then the entire behavior of the system is non-deterministic because of the interleaving of instructions. This can be done in any order. And you read from the latest write. So let's try to make things concrete. Now, this is a well-known model, and this is the model that we think of immediately when we deal with concurrency. So now I can define a run of this program as a sequence of events where each event corresponds to a particular execution or execution of one instruction of one of the processes. So for instance, here, P1 can execute its first instruction in which it sets X to 1 in the memory immediately, atomically. And then we record the event E1, which is exactly that, write instruction, write in the sense that you write to a shared variable. And maybe P2 now executes its first instruction setting Y to 1 in the memory. And this will be the second event in this particular run of the program. And then maybe P1 reads the value of Y and stores it in A. The value of Y is 1. So this is the latest value which was written to Y. So I take it to the process and stored it in the local variable A. And this is my E3, which is the third event, which is a read event because I read the value of a shared variable and stored it in my local variable A. And finally, P2 will perform its second and last instruction in which it reads the value of X, which is 1, thus obtaining the fourth and last event in this particular run of the program. So you see that here, I am not such, so this assertion is not satisfied. And in fact, you can show in this particular simple case that whatever interleaving you choose, you will not satisfy this assertion. And this is what we call mutual exclusion here. And as you will see that later, this simple program will violate this assertion later in other memory models than SC. So what's the advantage of SC? Yeah, in fact, this is what I'm saying. This is unreachable. We say that this particular configuration of the system is unreachable under the SC semantics. So the main advantage of SC is it's simple and it's intuitive. I mean, this is how you think about the the semantics that you think about, or you assume. In fact, most programmers assume the SC semantics when they write their programs, although the platform may not guarantee SC. The disadvantage is that nobody implements SC nowadays. And the reason is that it's too expensive. So it's unrealistic to assume the SC semantics, whether you are at the level of hardware, at the lowest level of system design, or at the level of a programming language, or even when you have distributed systems like geo-replicated systems, databases. All these kinds of systems, they will not guarantee SC because it's simply too expensive. So while SC is simple, it's unrealistic. And in fact, what I call weakly consistent systems, meaning systems that do not guarantee the strong consistency given by SC, can be found everywhere at all levels of system design. At the microprocessor level, if you look at your laptop or your iPhone or whatever, you see that they use processors in which SC is not guaranteed, in fact. Based on this observation, nowadays cache protocols are designed not to guarantee SC, but to give weaker guarantees, like TSO, CC. This is an example of a cache protocol, a recent one, which does not guarantee SC. And the idea here is that you get more efficient and you save energy because you do not need to guarantee the SC semantics. And this is also reflected in programming languages like C11 or Java, or in which you have semantics that are weaker than the SC semantics. And also in distributed data stores, like geo-replicated systems, they do not guarantee SC because it makes the system simply not efficient enough. So all these kind of applications, they induce new memory models, which are different from the other ones, and each of which come with a lot of complexities. So now one hot research area is to study these memory models that arise in these applications and to define new semantics for programs, concurrent programs running on such platforms, and also to redo verification testing and different analysis method, taking into consideration the new aspects that arise due to these memory models. Of course, in this presentation, I'll not be able to go through all of this, but rather than giving details of all these models, I will concentrate on one model, and in fact, one part of one model, namely the one of C11. So this brings me to what I call the release-acquired semantics, RA, in this presentation. So the motivation for studying RA is that it is relevant because it's part of the C semantics. And in fact, it's an interesting model by itself because if you look at people working with programming languages, they say you get a good balance between performance and programmability. So I'll not go through such details. The characteristics of the model is that it's much weaker than SC, but strong enough to make it sufficient for many for the design of many concurrent algorithms. And also it has, from the programming language point of view, it has verified compilation schemes to common architectures like TSO, Power, and ARM. So this is just a motivation. I will not go into the details, but I will introduce first the semantics of the release acquire to give you a flavor of a typical example of such of one MIC memory model. And then once I have described the semantics, I will also motivate why verification becomes difficult, or it becomes at least different from the verification of programs under SC semantics. So first, the semantics. And the semantics in a nutshell is based on what we call release and acquire. And this is why it's called the release acquire semantics. In fact, intuitively, you can say that the write operation now does not update the memory atomically, but it is seen as a release of a lock, if you wish. And a read is seen as an acquire of such a lock. So I will try to make this more concrete in the coming slides. But just remember that writes are release operations and reads are acquire operations. And if you read the value from a write, then you acquire the lock which is released by that write. So again, informally, you can imagine that you have a write instruction here in which you assign constant 2 to the shared variable x, and then you have some read operation in which you assign the value of x to the local variable a. Now let's look at a run in which these two instructions occur, and let's look at the segment of the run before the write instruction, which you call a, and the segment of the run after the read instruction, which you call b. Now if it happens that this read instruction reads its value from this write instruction, so which you call the read from operation, or read from relation rather, then what the release acquire semantics tells you is that everything, now this is very informal, the A segment happens before the B segment. So everything here, all the write operations before this write instruction or before this write operation are ordered according to the semantics before the write instructions that occur after the read operation. So this is the release operation and this is the acquire. So the write is a release and the read is an acquire if it reads from the write. So we say that A occurs or happens before B. So all the writes along A happen before the writes along B. And I will make this more concrete in a moment.
Hi, Parash, I
yes,
have a question.
There was a question?
So isn't that read should be A equal to X over there?
No. So it can be on other variables. And now this is very informal. I will make it more concrete later.
Okay.
So it can be on X, but it can be on other variables. For instance, if these writes are program order before the write here. And this I will make more concrete in a moment. At the moment, it's very informal, I agree, but this is the intuition. So let's try to make things more formal. So we do that by defining the operational semantics of the release acquire model. Again, I will not give any formal definitions. I'll try to illustrate it through some examples. So, and the main ingredient in the definition of the operational semantics is something which you call a view. Now, such a view is a description, of a write instruction. So a write instruction is not anymore an atomic update of the shared memory. It contains more information than that. So what we do is that we define a view, and the view contains the write instruction itself. So for instance, this is one view in which some given process is assigning 2 to the shared variable x. But in addition, assuming that we have 2 shared variables, x and y, this view carries some more information about the variables x and y. So the write operation is here, but we have two timestamps that are natural numbers associated to each variable in the system. Now, what these timestamps mean is the following. So these are logical clocks. So if you wish, you can see a write instruction or a write operation as the write operation itself, together with a vector clock, with one entry for each variable, where the entry contains a timestamp, which is a logical clock. And as you will see later, the logical clock for x gives you the age of the latest write on x seen by the process when it performed the write operation here. And symmetrically, the logical clock for y in this view, it's the age of the latest write on y seen by the process. So I'm trying to make things more and more concrete step by step. Still not clear, but the view is, the message to be taken from the slide is that such a view or such an operation, a write operation, is more complicated. You need more information to describe it, namely the view of the thread together with the instruction it's carrying out. So all this is to answer the question that I was asked just a couple of minutes ago. So let's take the notion of a view with us and now define the shared memory. So remember, in the case of SC, the shared memory was just a function which gave you the values of the variables of each variable in the shared memory. Now, in the array semantics, the shared memory is more complicated. In fact, it's a pool of views, which means that at any point of time, at any configuration during the execution of the system, you have some set of views, which you call a pool of views, and this will define the shared memory for you. So you see that we have a set of views, and now we have different processes, P1, P2, P3, P4, that are sharing this memory. So to define the operational semantics, now we define what happens to such a configuration of the system when I execute instructions. Remember, in the case of SC, when I did a write, I just updated the shared variable in the memory. When I did a read, I just looked at the value of the variable in the memory. And everything was atomic. Here, if you look at what happens, so let's just concentrate on P1 rather than giving the formal operational semantics. Suppose that I have P1 and it's performing these three instructions. A read from X, a write on X, and a read from Y. So let's look at the first instruction, which is a read from X. This is the semantics of read instructions. So first of all, if you look at a configuration of the whole system, you have the shared memory, which is a pool of views, and you have the local view or the local state of each process, which consists of the program counter as usual, but also some local view, which defines the view of the process, meaning that when the latest write on the given variable happens. So this is for X and this is for Y, and this is the local view of P1. So now in a read, what you do is that you select a view in the memory non-deterministically. So this is a non-deterministic aspect of the behavior of the system here. You select a view in the memory which corresponds to a write on the variable which you are trying to read. So in this case, P1 is trying to read the value of X. So this means that I go to the memory, select a view in the memory, performing a write on X. So the two relevant ones here in this particular case are these two, because these are writes on Y. So let's forget about the Ys. Now there are two candidates from which I can read the value of X. So the reading is not deterministic anymore. But I have some other conditions to satisfy. The variable timestamp, which is the timestamp for X, should be at least as recent as your timestamp, as the timestamp in your local view. So this means that if I look at my local view, P1 is trying to read X. Its timestamp for X is 3. Now it has to choose some message whose timestamp on X is at least 3. So this means that you exclude this message. So the only possible message to read in this case is this one here. In general, you may have several possible messages from which you can read, and in such a case, the choice will be non-deterministic. So now this message can be read, and we call this a readable message. And this I will come back to. So from this configuration, and given this instruction, this is a readable message. So now we do the actual reading. And how we do the actual reading is that by updating our local view. And the update of the local view consists of two parts. First, you do read the value of X, which will be 1 here, but also you update your local view by updating your view with respect to the recency of the write instructions that have been performed on the different variables. So concretely, what you do is that you look at your local view, you compare it with the view of the message that you are reading, and you take their least upper bound. So this means that you take their, you see them as vector clocks, and you take the largest or the larger of the two values per variable. So in this case, I have 4, 3, I choose 4, and I have 1 and 2, so I choose 2. So this means that the new local view of the process will be 4 and 2. And in particular, in general, if you read the value of a variable, this may update your view of the other variables in the system also, because you are taking the least upper bound of the entire vector clock. So this is the new local view with respect to vector clocks, but also you have to read the value of X, which is the one here. And now I have generated my first event, which is the reading of X into storing the value 1 in A. So you see that it's more complicated. So now this is my semantics for read instructions. Of course, this should be defined. I mean, this is an operational semantics, and it should be defined. It's defined through inference rules. I'll not do it here. Now let's look at the write instruction. So what you do is that you say that I am doing a new write instruction. So this means that I have to choose the timestamp or the value of the logical clock for the new write instruction. And what you do is that you create a new local view, and then you add the new local view to the memory. So more concretely, you create a new local view. So let's create a new local view in which we increase the timestamp for X. So this means that you have to choose a new variable timestamp, in this case for X, because this is the one I'm writing. So the new timestamp should be newer than yours, strictly newer, which means that something strictly larger than 4, but not in the memory. But doesn't need to be larger than everything in the memory. So you just choose something which is unique, but which is strictly larger than your timestamp. So in this case, I choose, let me see, a 5, because you see that there is no 5. The logical clocks in the views inside the memory for X are all different from 5, so 5 is fine. The concrete value I choose is not important, only it satisfies these two conditions. Now this gives me a new local view, and then I copy the new view to the memory, which means that I get a new message in the pool of messages. So this is the write instruction. And now I have generated my second event, which is E2. Finally, I do another read instruction. So you see that, sorry, I am doing a read on Y, which means that I have to choose one of these two messages. I exclude the writes on X. And then I have to choose something which is at least equal to 2. Here and here, we have 0 and 7. So the 7 is my only possibility. And now if I update my local view, you see that I will read the value of Y, but this will also update my view of X. So you see that if I take the least upper bound of these two vector clocks, then even my view of X has been updated, although I only read the value of Y. And now I take the actual value of Y, which is 5, and I generate the corresponding event. So this in principle gives you the operational semantics of release acquire, very informally described. So now let me first try to give you some intuition or feeling for the release acquire semantics before going into verification problems. So let's go back. I'll give you 3 examples if I remember correctly my presentation. So first, let's go back to Decker's protocol or the stored buffering example, and to see whether I can reach a configuration in which I satisfy the assertion, meaning in principle that I violate or I do not satisfy mutual exclusion for Decker's protocol. So suppose that we start from some initial memory where, in fact, this is the typical initial state of the system where all the values of the variables say they are equal to 0. And all the timestamps are equal to 0. And now I do a write on X, which means that I update my local view and I put the view in the memory. So I updated my local view. I chose something which is strictly larger than my original value, which was 0. And I put the message in the local, in the shared memory. I do the same thing for Y. So you see that my local view tells me that the value of Y is 0, the logical clock for Y is 0. So I have to choose something which is strictly larger than 0. Here, choose 5, for instance, and then I have performed the write instruction, and then I move the view to the memory. I updated my local view, moved the view to the pool of views. So now P1 can perform the read operation. And remember, the read operation requires that you choose something which is at least as large as your local or logical clock for the particular variable you are reading. Y in this case has a logical clock which is 0. So this means that I can choose either this message or this message, because both of them have logical clocks that are equal to 0 if you look at Y. So in particular, I can choose this message and take its value, which is 0, put it there, and then P1 is done. Now, because it doesn't need to update its local, or it updates the local view by 0, 0, means that it remains the same, but that's not very important. The same thing you can do for the second process, P2, it chooses this message to read for X, because the logical clock of X is 0, so it can certainly choose this message, read its value, which is 0, and now you see that suddenly this assertion is violated. So this, or reachable. So this means that if you look at, from the point of view mutual exclusion, Decker's protocol is faulty under the array semantics. So even if you take one of the most fundamental and basic protocols that we teach at the undergraduate level, it does not work anymore if you take one of the simpler memory models, which is the release acquire semantics. So this means that we have work to do. How to detect such errors and how to correct them. Yes, there was a question.
I have a question.
Yes.
Can you hear me? Aishwarya here.
I hear you, yes.
Is it so? This pool of views is always increasing. You never delete anything from the pool of views, right?
Yes, true.
Yeah, thank you.
Yeah. Okay, so so I don't delete anything from the pool of views, although some of these messages may be useless later because they are too old. I mean, all the processes have timestamps which indicate that they cannot read from these messages. You can do some garbage collection, but this is just semantics. It's not something that you implement, so that's fine. Anyway, so let me take you through one more example, which illustrates one aspect of the release acquire semantics, namely an important aspect of memory models, whether write events can be observed in different orders by different processes. Now, this is a property that's satisfied by. So if you ask this question, the answer is certainly no in the case of SC, because all the processes will see the write events in the same sequence because they have access, because these operations are performed atomically. But also the answer to this question is no for other weak memory models like the TSO model, if you're familiar with that. If not, it doesn't matter. But what I will show you here is that the RA semantics does not satisfy this property either. So the idea here is that there are two processes, P1 and P2, that are performing two write operations on X and Y respectively. And these two instructions, or these two operations performed by P1 and P2, will be observed in the reverse order by P3 and P4, meaning that P3 will think that P1 went first, and P4 will think that P2 went first. And to simulate this in our semantics, again, we start from the initial configuration where everything is 0. Let P1 and P2 perform their operations with the appropriate timestamps, for instance, 3 in this case. Put it in the memory. And for P2, you do this similar thing for Y, timestamp 4, and you put it in the memory. So in this case, these two processes have performed their write instructions, and the corresponding messages or views have been put in the memory. And now P3 and P4 start executing. So P3 will read the value of X and store it in A1. So it can choose this message, for instance, because the logical clock of X here is 3, which is at least equal to 0. So updates the local view and read the value of 1 of X, which is 1. Now it reads the value of Y, and now it can choose between this one, this message here, and this one, this message here, because its logical clock for Y is 0. And P3 being nasty, it chooses this message, or nasty. This is part of the semantics. So now you take the value 0 and you store it in A2. So now if you look at P3, it thinks that P1 went before P2 because it saw the effect of P1, which is the 1 here, while from its point of view, P2 has not performed the write on Y because it still read the value of Y, which was the initial value, which was 0. Now P4 can do a similar thing, but in the reverse order, reading the value of Y here, which is 1, updating its local view, and then reading the value of X, which is 0. So from the point of view of P4, P2 went first. So this means that P3 and P4 observed the operations, the write operations of P1 and P2 in the opposite order. So this assertion is reachable, which means that A1 is 1, A2 is 0, B1 is 1, B2 is 0, reflecting what I said, namely write events have been observed in different orders by the different processes. And this is possible under RA. So this indicates that RA is weak. In fact, it's different from SC at least, but it does guarantee some things. And in fact, if you look at people working with C, they say this is a strong semantics because, in fact, they use it for synchronization, the release acquired part of the C semantics. In the C semantics, there are constructs that are even weaker. And what it guarantees is its name, namely release acquired. And this is illustrated by a program which is usually, oh, sorry for the typo here, it should be message passing with an E here. So I don't know whether I need to fix it. Well, why not? So message passing. So what is that? Well, it means that what I told you before, and this answers the question that I was asked before. So let's see what it does. So first, you have this write on X. You choose a logical clock, like 3 here, and put the message, update your local view, and put the message, the write instruction 1 into the pool of views. And then you write 1 to I, do the same thing, choose a logical clock which is strictly larger than yours, say 2, create the corresponding message and send it to the shared memory and update your local view, which is 3.2 now. So put the view in the shared memory, and now you are done as P1. So now P2 starts working, and it reads the value of Y. Now suppose that, so now if you look at the value of Y, which is read by P2, of course it can read either this one or this one. But suppose that it reads this one. So now the choice is non-deterministic. But assuming that it reads this one here, then this means that it has read the value of Y here, because this is exactly the right instruction which was induced by the, or this is the view that was induced by this right instruction here. So if in the read instruction here, we choose the value of Y to be taken from this message, then you see that the value of Y will become equal to 1. Now the interesting thing happens. Now you have to update your local view, and you update your local view by 3 and 2, because you take the least upper bound 0032, which means that you get 3.2. So now what this happened, when this happens, this means that now P2 is aware of the value of X also. So as I told you before, by reading some variables, you may update your view on the other variables. So here I read the value of Y, but also in some sense, I also updated my view of X. So now I know that if I read the value of X, I have to take it from here. And concretely, if you look at the operational semantics, you see that if you try to read the value of X now, here, you are reading the value of X, it's not possible to take this value 0. Why? Because you want to take a value which is at least as recent as your logical clock for X, which is 3 here. And this disqualifies this message. So the only possibility is to take the value of X from here, which is 1, which means that this assertion is unreachable. So this configuration is unreachable. And this is a concrete example of what I call release and acquire. So this means that once you have this synchronization between the release and acquire, the write here, in some sense, occurs before the read here, which means that if you perform this read here, you see this value of X and not its initial value. And this is an explanation of what I told you informally before. Of course, this is still informal, but I hope this gives you an idea about what I mean by release, acquire, and acquire. So this is before and this is after. So any questions up to now? Okay. So very well. So now we have defined the release acquire semantics. We know some of its properties. What can we do from the point of view of verification? In fact, this example is related to the question that was asked before, namely, will the pool of views grow unboundedly? And in fact, yes, just take this simple program in which you have a self loop in which you do a write 1 to X all the time. So now taking our semantics, what you do is that if you unfold this while loop, so this is just an unfolding of the while loop, each write instruction will give you a new view in which it says my internet connection is unstable. I hope you hear me anyway. So you generate an unbounded set of views. And even if the program is finite state, which is certainly the case here, you have only one instruction and one value, one variable. So this is a finite state program, one of the simplest programs that you can imagine. although it's finite state, it gives you the operational semantics. It gives you the operational semantics gives you a transition system which is infinite state. So the state space is infinite. And in fact, this means that you have to now, of course, finite state concurrent programs have decidable verification properties under the SC semantics, but now this is not clear anymore. Given new weak memory models, for instance, the array semantics. And in fact, we have shown that even for finite state programs, the checking reachability of process states becomes undecidable. So all interesting verification problems become undecidable under the array semantics. So this means that if you want to do verification, you cannot solve the problem in general automatically. And this brings me to approximation techniques, which are very relevant, very interesting, at least in the context of weak memory models, but I believe also under the SC semantics, where you get more pragmatic. So you try to get more efficient by either considering over approximations like abstraction techniques, or under approximations, and there are techniques for doing that, like bounded context switches, and the subject of today's lecture, which is dynamic partial order techniques or stateless model checking. So I'll just give you a flavor of deep OR techniques and what they mean. So what's a dynamic partial order technique? So here, what we do is that instead of doing operational semantics, we work with traces. So let's consider the SC case first. So in fact, Kumar, I think I will need 5 extra minutes. Is that fine to say something meaningful?
Yeah, sure. I think you can. We have a half an hour break in any case. Sure.
Yeah, and if anybody wants to leave there, I mean, I will not be angry. So what does it mean? So if you go back to SC case, what we do by stateless model checking or in deep OR frameworks is that we are more pragmatic. So we consider threads or processes that are concurrent, that are loop-free, and that are deterministic. So this is a typical example of such a program. And now I take the case where we have again shared variables, X and Y, we have local variables, A, B, C, D, and then we have the interleaving semantics to start with, and then we have some assertion. So now we have the run, as I explained before. And now I define a notion of what I call a trace. And the reason why we would like to work with traces is that they are more efficient than working with runs, in a sense that I'll make more concrete in the next slide. And they're also nice, they are abstract, since they allow to treat different memory models in one uniform framework, as I will explain again in a few minutes. So in fact, if you look at traces, what you are doing there is that you are defining semantics for the model rather than having an operational semantics. So what's a trace? Well, a trace is a graph. If you look at the graph, you have a set of nodes, this is the set of events. So a trace captures a run, in fact, or a set of runs. Each trace captures a set of runs where the set of nodes in the graph corresponding to the trace is a set of events, or the set of events in the run, you see here. And if you look at the edges, the set of edges correspond to a set of relations. In fact, we have 4 relations on the set of nodes or the set of events. The program order, which defines the order in which the instructions are performed inside each process. So here you see that I have these 2 events here, X assign 1, A reads the value of X, which is 1, corresponding to these 2 instructions. And you have a program order edge between these two events because they correspond to the order in which the events are performed by the same thread. And you have one for thread 2 here also. You have the read from relation, which defines for each read instruction or for each read event, the write event from which it fetches its value. So in this case, there is a read from edge from this event to this event because this read event fetches its value from this write event, namely the value of 1 for x. And the same thing between these two events. You have the coherence order, which is an order on the write instructions. And this coherence order tells you the order in which the system believes that the write instructions occur. So now if you look at the coherence order, it's the union of different coherence order relations, one for each variable x, where the relation on each variable x is total. So this means that for each variable x, if you fix x, you look at the write instructions on x, then there is a total order on such write instructions. So in this simple example, we have only write instructions on x, and the coherence order these two write instructions on x. Finally, you have the from read relation, which is derived from the coherence order and the read from relations. So the intuition is that the from read relation tells you for a read event, the write event which destroys the value it's reading. So if you look at this read event, it's taking its value from this write event, and this write event is the next in coherence order. So this means that the read event here should occur before the write event here in order to be able to read the value given by the write event here. So again, there is an edge from a read event to a write event through the from read relation if the second write event here is coherence order after the write event from which the read event is reading. So if you don't understand all these things, it's fine. Just give you a feeling. So now the nice thing is that now I can define the SC semantics equivalently using the notion of traces by saying that a run is SC if I construct its trace, which is unique here. And if the trace is cyclic, then I say that the trace is SC, it satisfies SC. And I write it like this. So this trace tau satisfies SC because there is no cycle if you look at these relations, the union of these relations. And I say that this run satisfies the trace SC. So now the nice thing with traces is that they are sufficient for checking assertions, because if I have an assertion, to check whether the assertion is satisfied or not, it's sufficient that I look at the read from relation to check for each read instruction the value of the write, which it read from, and then I use these values to check to evaluate the assertion whether it's satisfied or not. So this is the idea of DPOR, dynamic partial order reduction analysis. You construct the traces systematically, and by checking the traces, you know whether you are violating the assertions or not. The second advantage with traces is that they are more compact than runs, in the following sense that you may have different runs that have the same trace. For instance, in this simple case, I have two runs that are different, but they're only different in the sense that you only reorder to read instructions that are reading the same values. So both these two runs have the same trace here. So the trace is not sensitive to the order of read instructions here. So at least this is one aspect of traces that give you a more compact representation of runs. And this will be crucial in the design of DPOR techniques. So these two runs satisfy the same trace. So now what's dynamic partial order technique? In fact, I just defined the technique and then I will stop because I will not have time to go through the details. I just define the problem and then tell you what we have done for array. So the idea here is that if you give me a program consisting of a set of threads, then I have what I call an optimal deport. It means that if you give me the program, then I have designed an algorithm which generates one and only one run per trace. So this means that what you do is that you, if you know Mazurkiewicz traces, you generate one representative for each Mazurkiewicz trace, and then you analyze the traces that you have generated to check whether you have violations. So this means that if you have the program that I showed you before, it has 4 traces, and then it has 6 runs. But some of these runs, as I said, correspond to the same trace. So what the optimal deport does is that it generates only one run per trace. So this means that it chooses one of these 2 and only generates one of these 2. So it generates 4 runs for you. And this is sufficient to check whether you are violating an assertion or not. And in general, the number of traces is much smaller than the number of runs. And this is crucial for efficiency of the algorithm. And in fact, something which in the presentation I call super optimal, this is not something that we use in the paper. We go one step further and we say that if you have 2 traces whose only difference is in the coherence order, then from the point of view of violation of assertions, this doesn't matter, because the only thing which matters is to have the program order and the read from relation. So this means that if you have 2 traces whose only difference is in the incoherence order, but otherwise have the same read from and program order relations, then you should not distinguish between them. And in fact, what we do in super optimal deport is that in this case, we generate only 3 runs rather than 4. But in general, we are talking about thousands of runs. So this is again crucial from the point of view of optimality. So finally, so this is a super optimal deport, which means that you only generate traces with different program order and read from relations. So we say that let's consider SC. So what we have done is that we did this for SC, and now we extend it for array. So again, what you do here is that you define axiomatic semantics for array. Now for array, what you do is that the only thing you do is that the axiomatic semantics will be different. So this means that instead of taking the union of coherence order for all the variables and the union of from read X for all the variables, you just check a cyclicity per variable. I only give one example, and then I will just give you the results of some experiments that we have done for array. So suppose that we have this program here, this thread, I'm constructing a trace for this, for one execution of this program. So first we have this trace here, or these 2 events generated by this thread here, program order between them. You have these 2 events generated by this thread here, program order between them. And the same thing for the first thread here, and the same thing for the last thread here. So these are the program order, or this is the program order relation on the set of events. Now the read from relation, this read takes its value from this write. So I have a read from edge. And this read takes its value from this write, a read from edge. And the same thing here, and the same thing there. Now coherence order, I take this write on X to be after this write on X, and I take this write on Y to be after this write on Y. So now I have program order, read from relation, and coherence order. I can derive the from read relations as I described before, like this. You get these 2 edges. And now, in fact, if you look at this trace, you don't need to check it on the fly, But if you look at this trace carefully, you see that it satisfies RA because you don't have cycles with respect to this relation for the variables x and y. So if you take program order read from, coherence with respect to x, from read with respect to x, there is no cycle. And the same thing for y. But it does not satisfy SC because of the cycle here. So the main difference here is that in SC, we mix the variables. We take the union of the coherence order relations with respect to all the variables, while for RA, we take it per variable. And you can show that this axiomatic semantics as defined here, it is equivalent to the operational semantics that I showed you. And now you can redo the exercise for DPOR using the release acquire semantics and using this axiomatization of the release acquire semantics. So of course, I will not go through the details. I will just, what we have done is that we have defined a DPOR framework for the release acquire semantics, which is sound. So it only generates traces that are valid with respect to the array semantics. It's complete. It generates all valid traces. It's optimal. It only generated traces that have different program orders and read from relations. And it's deadlock free. This I will not go through. This is a detail for DPOR. I just wanted to say that this is not only theory. I mean, the algorithm, as you can find in the papers. So we have a tool that's available online if you are interested, and we have made an extensive set of experiments on different examples in which we compare with state-of-the-art tools. But just to give you some conclusion, so I just gave you a flavor of the challenges that arise when you have memory models that are different from SC. These memory models are, on the one hand, relevant. They occur everywhere, but they are different from SC, which means that now we have to redo our thinking. We need to define models, semantical models, and computability, decidability, complexity, and then redo testing and verification and then approximation techniques, abstraction techniques. And what we are doing now is that we are considering these frameworks for the full C11. Release acquire is a subset of C11. In fact, for SC, some problems become even more difficult than these weak memory models. For other models like TSO, power arm, causal consistency, we are thinking about weaker notions of traces and also other properties that are interesting. In fact, we are working with race detection and to check other properties than safety, like liveness, progress, and termination. Sorry for taking too much time, and thank you very much for listening. Any questions are welcome.
So, I mean, anyone with a question could just unmute themselves and go ahead and ask. So I had one question. So this, since you say this, the reachability problem is undecidable. So when you do this DPOR, whatever you get in the end is again run under this semantics, or so what is the object that you generate through
so,
the reduce through?
So you see that, okay, so let me go back to the slide. It's a good question, in fact. Let me see where I have the DPOR. Here. So you see that the thing for DPOR is that you do this as under an assumption that the programs, you don't have loops. So if you have any loops, you have to unfold them for a given number of times.
All right. Okay.
And all the processes are deterministic. Okay. But you guarantee that you generate all the interleavings that are possible. So the only source of non-determinism is the concurrency. Okay. So you guarantee that you cover all the possible interleavings. Now this loop freeness, you can relax it, but then you get a different framework.
Okay. So I had one more question before So I have one more question. So you had said that this model in some sense can be translated into the other models. I mean, you can generate code in TSO and so on. So does it mean in some sense that the reordering there is more stringent? In some sense, you have to impose restrictions on this model to get those? Can you get it like that?
No. So what I said is that you have compiler schemes. So this means that if you give me a program which I interpret over the release acquire semantics, then I can define my compiler so that I can run it on a TSO processor, and it respects the semantics.
Okay.
So this doesn't mean that they are computationally equivalent, in fact, or one of them is easier than the other.
So there's no way to actually, okay, so you cannot translate, for example, any decidability or
no, in fact, they are provable. I mean, you can have examples where one of them give you some behaviors that the other cannot.
Okay, thank you. So if anybody else has questions, I will let them also ask questions.
Yes, I have one question.
Sure.
Hi, this is Pierre from Madrid. So I have a question about the specific properties and the partial order reduction. So so the reduction is the same regardless of the assertion you check, no? And is there any research on further reducing based on the specific property you're looking at?
No, it's generic, so you don't need to have the property.
It's generic up to the class of properties, right? So reachability, you do something like that.
Yes, exactly.
Okay.
For race detection, you may need to do something else because you may use. Yes, exactly. Yes. But I mean, if you say I have a language for assertions, then the algorithm is the same for all the assertions that you might use.
So are there any other questions? Or?
Yeah, maybe I can have one. It's Igor here, Igor Walukiewicz.
Hello, Igor.
You mentioned other memory models. Are they also characterized by these axiomatic schemes on traces? How is it done?
In fact, both operational and axiomatic. You can have both models.
So all of them are characterized by orders, by some axioms on these 4 orders that you mentioned.
Yes, or variants. I mean, you may use other relations than program order or read from. So these are
okay.
So the orders are not the same. In fact, for some of them, they don't respect program order. So you need to have some more refined relations on the instructions from the same thread. Like you may say that I have data dependency, which means that for some instruction to execute, for some memory address, you have to be able to compute the address of the memory. And you induce other types of dependencies, and this will be reflected also in the characterization.
Mm-hmm. Thanks.
Okay. So are there any other questions? Okay, there are no other questions. We'll thank Parosh for a very nice talk.
I have a question.
Oh, sorry. Oh, sure. Yeah, please go ahead.
Sorry, so it's Anka. So, hi Parosh. So, just wanted to know how this model, RA is implemented consisting these bags. So it looks like not being something that you can implement efficiently. A bag of views with choosing comparing.
In fact, they are not. They are not implemented. I mean, this is just a model. And then when you compile to some architecture, you show that you respect the semantics. And what you typically do is that you say that if I have certain conditions on the program, then I go back to SC. So if you don't have races, for instance, if you don't have any races in the program, then some of these models, they behave like SC. So you don't need to consider all these aspects when you program. So this is just to define the semantics. But when you have a compiler for such, you don't implement the semantics as such.
But on the processor, so you need to have some
on the processors. In fact, on the processors you have like TSO, And then it will be more efficient because although the model itself, if you study the model, is more complicated, what at the processor level it tells you is that you can reorder operations. So for instance, you can say that when I do a write instruction, I don't need to wait to get acknowledgement from the memory that the write instruction has been performed, which means that the process can go to the next instruction. And in such a way, it becomes more efficient. But you get more interleaving. So if you want to reason about the program that runs on such a processor, then the behavior is much more complicated. But the execution of the program itself is more efficient.
Okay, thanks.
Yeah.
All right. So
I have just one question, if I can.
Okay, sure. Let's take the last question. Okay, go ahead, please.
So in the views, you have like the logical clocks for, so there is a logical clock for every variable. So I was just wondering what happens if one considers one logical clock across all the variables. Does it boil down to a C, or it will give another memory model which might be more restricted than the release accuracy?
So what's the question again? Can you take it a bit more loudly so that I hear? So what if what? I mean, I understood the introduction, but not the question itself.
So instead of having one logical clock per variable, so if I have a logical clock for all the variables, like if I have a common...
One logical clock.
Yes, one logical clock. So will it boil down to the SC memory model, or will it give something interesting? Or...
No, so then it will be like total order. So it's like SC.
Yeah, okay. I was just, that was the question. Thanks.
Okay, so we'll thank Parosh again for this very nice talk. And we have a 14-minute break, and then we are back here at 3 o'clock for the next talk.
I apologize again for taking...
Oh, no, it was very nice.
Thank you very much.
Enjoyed it. Thank you.
Thank you. Thank you, man.
Hi, Carolina. Hello. So maybe you should check out the slides. I'll ask the host to make you co-host, so you can do that. Let's see. Okay, so you can.
Can you also see my pointer?
Yes, it works. Works well.
That's very good. Should I leave that there or?
Sorry?
Should I leave that there or should I let stop sharing?
Yeah, it's fine. We can see it move. So.
So this morning my internet was being very unstable on the previous talk.
In fact, during Parash's talk, I got thrown out once and came back. So
okay, maybe it wasn't completely my internet's fault. Okay,
yeah,
I'm hoping
so
that.
my internet has been not very good. I hope it'll be okay. Yeah. Well, for the speaker, it's worse. So
yes, but I've rebooted everything, and for the time being, it seems to be okay. I might remove the video if it.
Oh, by the way, is it Carolina or Carolina?
Carolina.
Lina, because of the two. I mean, the Finnish two E's there, right? So I was wondering if that meant
yeah, well,
different.
yeah, like the Finnish pronunciation is Karoliina.
Okay. So it's not a longer E.
So, I mean, in Finnish, it is a longer E than it would be without. But I don't think English pronunciation makes the difference there.
Well, in Indian thing also, it would be in general longer.
Yeah. So in Finnish, it's the difference between Karolina and Karoliina.
Yeah. Oh, by the way, that my language is Tamil. This is from South India, and Tamil and Finnish are supposed to have some common components. I mean, Tamil, Finnish, and Magyar. There are some common things that linguists have found from history. So.
Oh, that's interesting.
Do you know Ralph Johann Bach? He did some work on this in the 90s, I think.
Oh, okay.
Yeah, so he was the one who told me about it, and then I read about it.
So I assume well, I don't know, do we know whether, I guess they have to be somewhat coincidental. I can't imagine there's a...
No, there is, because, Tamil is also not Indo-Germanic, Hindi, they're all Indo-Germanic languages. Tamil is a Dravidian language and it has a different history altogether. But then what connects these? I mean, those things I don't know. Linguists have theories. Okay, so let's see. Maybe all these guys are in gather, and there must be some way of going and clapping. Usually, that's what one does, right? Go to the coffee room and clap.
Yeah.
Tell people to come for the session. So, but I guess they'll show up now. Prakash,
yes,
are you here? No, I think he's also in gather.
Yes, I'm here.
Prakash.
Hello.
So
no, I'm here.
Almost time. Should we?
Yeah.
So you should be the one clapping and gather to tell people to come.
Yeah, sure. I'll go ahead and I will try to.
So shall I start, Prakash? I think the host should be told to start the recording as well.
Yes, I will gather all people here.
Yeah. Okay. So.
Yeah, you should be able to start. I mean, if there are anybody, then I bring them here.
Okay, just one moment. Okay, so welcome everyone to the second session of the workshop. And it's my pleasure to introduce Dr. Carolina Lehtinen from University of Liverpool. She's from Finland, but grew up in France and learned logics, I believe, in University of Cambridge, and did her PhD in Edinburgh. And after postdoctoral work in Germany, she's been in Liverpool, which she calls sunny. But I must say that every time I have been in Liverpool, it has rained all the time. So, yeah. And she's been involved in a cleanup operation on monitorability, bringing some order into the zoo of concepts that seem to afflict runtime verification. And she's going to tell us all about it. And it's a pleasure to have Carolina here. Over to you, Carolina.
Thank you very much for the introduction. I'll mention that this is my last talk where my affiliation is the University of Liverpool. I will be moving to CNRS in Marseille in January. But, you know, for the time being, we're still in Liverpool. So yes, thank you very much for the invitation to have me talk about monitorability, so which is one of the cornerstone notions in the theory of runtime verification. So this will be a kind of gentle tutorial on this topic. So when we study monitorability, we ask, the idea is to ask which specifications can be verified at runtime. But when we ask this question, very soon we run into a slightly deeper question, which is, well, what do we actually mean when we ask whether a specification is monitorable? And that's the question I'd like to dissect with you in the hour to come. So if you come from a verification background, you're probably familiar with model checking and theorem proving and static analysis and all of these verification methods which look at a system and try to prove some properties of that system before then sending it off to deployment so that you have some guarantees about how it is going to behave. In contrast, in runtime verification and runtime monitoring, the idea is to try to verify a system without actually looking at the system itself. So we doing verifications in a situation where we don't have access to the program or a model of the system itself. So this might be the case if you're building an airplane or a car and you have some components that come from third-party providers who don't want you to actually look at their code because that's intellectual property. And they want to reassure you that, oh, you know, this component, we've checked it, it is doing what it's meant to be doing, don't worry about it. But of course, when you're putting that component into your airplane, you would like to have some additional assurance that it's actually going to behave according to some boundary conditions so that you don't end up crashing your plane, for example. Another situation in which you won't have access to the system itself is after you've deployed a system. So now we've done all of your static analysis and you send your component on its way, it's working, it's executing, and instead of just hoping for the best, you probably do actually care about monitoring it as it is running so that if something does go wrong despite your best efforts, rather than letting your car drive off a cliff because one of the components is behaving in unpredictable ways, you can have some sort of alert and revert back to a secondary pilot or something like that. So once you've deployed a system, that doesn't mean that verification is over. We can still look at runtime verification once the system is in place. And of course, sometimes these static methods such as model checking, they're just quite expensive. And if your system is updated, gets updated a lot, sometimes it is in your interest to try to use cheaper methods than full model checking so that you can try to catch errors early before having to go through a very expensive verification process. And all these situations, you're not going to actually look at the system, so you're going to turn to runtime verification and looking at what you can do there. So the common theme here is that we're not going to look at a system, we are going to look at its executions. But even then, we're not going to look at the whole execution of the system. For example, if you have a component running in your car, you're not going to wait for the car to crash and then look at what happened in the executions. No, you're going to look at finite prefixes of the execution as the execution happens, and you're going to have to use that partial information to make deductions about this whole execution, which could be infinite. So you have a very small amount of information that you need to use and do your best with. So because you have such a little amount of information, we can think of runtime monitoring as a kind of cheap and cheerful approach to formal verification. It is cheap because, well, the information you have is a finite prefix of an execution. So all your computations are going to be much simpler than if you are doing model checking and where you end up with your state explosions and all of that very expensive work. So it's cheaper, but the flip side of that is that you also get fewer guarantees than you would get if you're doing model checking. So of course, since you have such a small amount of information, you can't expect to get full answers about correctness because, well, you don't have the full information. But sometimes in these situations where we don't have access to the system, it's the best we can do. And the idea is to make the most out of this very limited amount of information we have. Now, we are still within the realm of formal verification, so we would still like to do things properly and do things rigorously and have a good understanding of what it is that we are doing. So in particular, we would like to know what guarantees our runtime verification tools can give us. We know they can't give us the same guarantees as model checking, but we would like to have some kind of understanding of what is actually going on. And we would like to know how the specifications that we are verifying, how those affect the guarantees that we can get. So this is where the study of monitorability comes in. We ask, what are the guarantees that we can get for different types of specifications, and what other parameters affect this set of monitorable properties. So these are the questions we'll dissect in this hour. Now this is based on work I've done recently with Luca Cetto, Antonis Achilleos, Adrian van Colenza, and Anna Ingolsdottir, so a collaboration across Iceland, Italy, Malta, and wherever it is I've been. But also it is very largely based on a lot of very classic literature on runtime verification and all the great giants that have worked on those. And so it is a kind of mix of very classic things and some kind of recent twist on how we can understand these classic notions. The plan for today is that, well, we'll start looking at what a monitor is as an object, what they can do, and more interestingly, what they can't do. Then we'll talk about specifications and, more importantly, the relationship between these monitors and the specifications that they are trying to monitor for. And this will give rise to various notions of monitorability. And then we'll look at how different parameters of our setup, so what kind of monitors we look at, what kind of domains we work with, how those will affect what is monitorable. So monitors, so as I've kind of described, the setup is that we have a system, we treat it as a black box, we don't look inside, but our system is going to produce an execution event by event, and our monitor is allowed to look at those executions as they come out of our system. And our monitor, as it reads these, at some point, it can say, stop, I have seen enough. Well, it doesn't say stop, it says, okay, I have seen enough. I know that this execution is bad, and it will give us a negative verdict, or it might wait a while and say, I have seen enough. I know that this execution is a good one, and it will say yes. Or the third option is that our monitor will just keep going and never say anything. So we also have the inconclusive verdict, which tells us precisely nothing. And we'll see that those are all three necessary. So the pillars of this setting is that a monitor will always give a verdict, well, it won't always give a verdict, but if it gives a verdict, it gives this verdict after observing only a finite prefix of a potentially infinite execution. So we reach a verdict within a finite number of steps. And once we have reached a verdict that is final, it is irrevocable. I can't change my mind. And that's so that's the kind of high level idea of what is a monitor. It is an object that satisfies these two restrictions. Now, you can then implement monitors in many ways. In this talk, I'm going to use as examples a very simple set of monitors that are finite state programs with 3 verdicts. So here, I'll describe monitors like this. So a monitor can either be a question mark, which is our inconclusive verdict, which corresponds to a monitor saying, oh, I don't know what's going on. We have the negative verdict, which is a monitor saying, I know that this is a bad execution, and we have the positive verdict. And then our monitor is just a program that can reach one of these verdicts. So it can observe an alpha and proceed. We have some non-determinism, and we have some recursion. So if my monitor is X, then it can proceed as M, where M is the monitor bounded by X. So a very kind of simple process algebra that describes the behavior of a monitor. So we can use this to write down some monitors, and we can give those some semantics using operational semantics. Here, I'd like you to mostly pay attention to the 2 rules at the bottom. So here we have this rule that tells us that if our monitor has reached a verdict, then it can observe any event and it will remain with this verdict. So this is an operational rule that enforces that our verdicts are irrevocable. Once I reach a verdict, I can't change my mind. And then we have this final rule that says if my monitor can't proceed when it observes an event, then it has to give up and it will reach this inconclusive verdict. So if it doesn't know what to do when observing an alpha, it's just going to reach the question mark verdict. And otherwise, it proceeds as any program would by, say, observing alpha and proceeding, and so on and so forth. And we can use these semantics to give describe the behavior of monitors, turn them into transition systems. So for example, here we can write down this monitor, and then it's to describe its behavior, saying if it sees a shutdown, it will reach the positive verdict. Now, if it reads a request followed by 2 acknowledgements, then it reaches the rejecting verdict. And then we say that a monitor accepts a trace if it reads the trace and reaches the positive verdict. And here note that our traces can be infinite or finite, but because of verdict irrevocability, a monitor will accept a trace if it accepts some prefix of that trace. And conversely, we say that a monitor rejects a trace if it reaches a rejecting verdict with some prefix of it, and then it will remain in that negative verdict. So, for example, here we have a monitor that, and here we have a trace that it processes, and we can see that it can process try and then proceed. Sorry about that, and then proceed as X. So we can process our 3 tries, and then when it processes fail, it will reach a rejecting verdict. So we say that this monitor rejects this trace. And I note that I will use the omega in the exponent to say that success occurs infinitely often at the end. So this trace is rejected by this monitor. Here's another trace. Again, our monitor can process the 3 tries, and then when it processes success, it will reach an accepting verdict. So we say that this monitor accepts this trace. And in our third example, if our monitor keep saying try forever, then it will just keep going and never reach a verdict. So I will use omega to write that the monitor is does not terminate or does not reach a verdict on this trace. So there are in fact two ways for a monitor to be indecisive. It can either reach the question mark verdict, or it can not terminate, in which case it will keep reading our trace, hoping or waiting whether eventually it might see a success or a failure, but maybe it will just keep going forever and also be inconclusive. So this monitor here, we can describe its behavior as follows. It rejects if on our trace fail occurs before success, and it accepts if success occurs before failure, and otherwise it is inconclusive. A second example, here we have a monitor. If it reads 2 acknowledgements, it can proceed. Once it reads a request and a second request, it will reject. So here we have a monitor that rejects our first trace. And I'll give you about 15 seconds if you want to think through what happens in this second trace. Okay, so here what happens with the second trace, well, our monitor will read the request, the first acknowledgement, and then the second acknowledgement, and start again. So this monitor does not terminate and will be inconclusive on this second trace. And we can describe the behavior of this monitor as follows. It rejects traces where we see 2 requests in a row. And this is our final example, where we have a monitor that can read act twice. Then if I see a halt, I will go into the second part of this monitor, where it can process another halt, and this time it will stay within this second part of the monitor. And then when it sees resume, it will start again from our X. So this monitor can process this trace forever and not reach a rejecting verdict. On the other hand, if it processes this trace here, it will first process the act, then with the halt, it will enter the second part of the verdict, where an act will lead to a rejecting verdict. So it will reject this second one. And finally, what does this monitor do on this final trace? Well, it can observe the act and proceed, but then it sees resume. And here the only actions that it knows how to process is act and halt. So when it sees resume, it will reach this inconclusive verdict. It has to give up and say, I don't know what to do about this trace. So we can describe the behavior of this monitor as follows. It rejects if once we have seen halt, act occurs before resume. And it is indecisive if resume occurs before halt. So you can think of these monitors as kind of simple finite state automata, if you like, automata, but which have this kind of three valued semantics rather than the usual accept, reject semantics. Okay, so those are monitors. Writing a monitor down does not mean that it does anything sensible. For example, here is a monitor that comes from our syntax, but it both rejects and accepts a trace that starts with a request, which doesn't sound like a particularly useful object. So here we've defined one way of implementing monitors that satisfy these 2 monitoring properties. Namely, these are monitors that reach a verdict in a finite number of steps, and once they reach a verdict, those verdicts are irrevocable. However, we've made a bunch of decisions, and this is not the only way you can think these are not the only monitors you might want to think about. In particular, the monitors I've shown you, they are finite state, so they're in some sense regular. They don't have, say, a stack or a queue. They don't have registers, and so they're limited in their computational power. The alphabet that we use is finite, which means that they can't handle data. So if your events had some integer data, well, these are not the monitors that can process any information about those. But of course, you could add registers and comparisons and see what happens there. And then these are a slight kind of interesting and important detail is that these monitors are not able to observe whether an execution has ended. And this is an assumption in our setting, is that, well, if my monitor observes an execution, it only looks at the events, and it might not know whether the execution has reached an end, either in a way that fails or in a good way, because, well, our system might be idle for it can be idle for as long as it wants, and that may or may not be an accepted behavior. So if we have a system that responds to requests, then if there are no requests, then it is perfectly acceptable for my system to be idle, and essentially the execution is finite. However, my monitor has no way of knowing whether that is the case, whether my system is just waiting for something to happen or whether it has reached a deadlock. So this is the limitation of the monitors that we consider here. Okay. So we have our example monitors, which analyze our executions, potentially reach a verdict, and once they have reached a verdict, these verdicts are irrevocable. And now what we are going to do with these monitors, we're going to think about how much they can tell us about our systems and the specifications that we try to verify. So we're going to study the relationship between the monitors and the specifications. So of course, these monitors, they don't just appear from the void. Ideally, we want to synthesize them from some high-level specification so that we have some precise guarantees about those specifications once we deploy our monitors. So here, our specification is just a set of traces. So for example, the traces in which eventually success occurs, the traces where a failure event never occurs, traces where every request is eventually followed by an acknowledgement, traces which either end with a shutdown or where reset occurs infinitely often, or even traces where brackets are well matched. So here are a couple of things to note. In this talk, I'm mostly going to use regular properties as examples, so the ones you would get from your favorite temporal object. But that is here. We can, of course, consider much richer specifications, such as brackets are well matched. That's a context-free language. And again, our specifications can involve finite and infinite traces. So here the fourth specification, either trace ends in shutdown or resets infinitely often. Here we have a specification that accepts some finite traces, but not all of them, and accepts some specification that holds on some infinite traces and not on others. So in other words, we don't just consider finite traces or infinite traces, but we consider this set of what I call finite traces, which is a union of finite and infinite traces. So that's also a difference with the kind of quite often real automata theory or logic will work either on finite or on infinite traces, but in the setting of runtime monitoring, we do often want to consider both finite and infinite traces. Now, since this talk is only an hour, I am going to use natural language to describe specifications, but of course, you may pick your favorite formalism to describe where languages over words, whether that's a temporal logic, an automata model of your favorite type, or a grammar. And then we can ask, well, we have specifications, we have monitors. So now what does it mean for a monitor to be correct for a specification? And then once we have answered that question, which specifications have correct monitors? And here what is tricky about this question is that on one hand side, we have specifications which have this two-valued semantics. Either an execution satisfies a specification or it violates it, and there's no other third option, while as we have seen, our monitors have a three-valued logic where they can accept or they can reject or they can be inconclusive. And the correctness of a monitor, what we conceive as the correctness of the monitor, has to somehow relate this three-valued semantics to the two-valued semantics of our specification. So one notion of correctness we definitely want is soundness. So if you have a monitor that reads a finite prefix of your execution and says, I have seen enough, this trace violates my specification, you would ideally want that to be true. You would like to know that this execution and all the possible completions of this execution do in fact violate your property. And conversely, if your monitor says, I have seen enough, this is a good execution, then you would like to know that indeed, whatever happens next, all continuations of this finite execution are indeed satisfying your specification. So this is the notion of soundness. So we can say that a monitor is sound for a property if for all traces we have this implication. So if my monitor accepts a trace, then the trace should be in the specification. And because we have this property that our monitor gives its verdict after a finite trace, this also implies that all continuations of our traces should be in the specification. And conversely, if the monitor rejects, then the execution and all its continuations should be not be in our specification. For example, if we have a monitor that observes a beta and accepts, this is sound for the property that alpha does not occur next. Since alpha and beta are mutually exclusive, if I see a beta, then I can be reassured that I did not see an alpha. Not beta is also sound for alpha never, though it is not sound for alpha never occurs. If I see a beta, I know that alpha did not occur in the first, as the next event, but it might be the case that it occurs sometime later. So this is not sound. If I have the monitor that observes an alpha and then rejects, this on the other hand is sound for the property that alpha never occurs. But so is this more powerful monitor, which can observe as many betas as it needs to, and then if it ever observes an alpha, it rejects. That monitor is also sound. Now, soundness, that seems like a very sensible property to want. However, it is also extremely weak. Namely, there's a monitor that is sound for all the specifications there are. So the monitor that never gives a verdict, it's trivially sound for everything. In other words, if you, as a notion of monitor correctness, soundness is surely necessary, but it is also very weak. So if you ask me for a monitor and you only want it to be sound, then I'm really not giving you very much if I just give you this inconclusive monitor. So we'd like to have something stronger. Now, usually when we have soundness, we also look for completeness. So we can try to do that. And the kind of first definition of completeness you might look for is the following. You say, well, ideally, I'd like it to be the case that if my execution is in the language of my specification, then I'd like my monitor to be able to tell me that and say and accept the trace. And conversely, if my trace violates my property, then surely I want my monitor to be able to tell me and reject it. So this is the kind of a notion of completeness. But the problem with using this kind of completeness in runtime monitoring is the following. Well, imagine you have a specification which has a sound and complete monitor. And now you read the empty trace. Now the empty trace maybe it is in your specification, maybe it isn't. If it is, then since your monitor is complete, your monitor should accept the empty trace. But then because of the irrevocability of verdicts, your monitor now has to accept everything. And then since your monitor is sound, well, actually your specification has to contain all executions. And conversely, if the empty trace is not in your language, then your specification has to be empty. In other words, the only specification that admits both sound and complete monitor is they are both trivial. So this is a very strong, asking for completeness in the context of runtime monitoring is much too strong, as then you only get trivial properties that are monitorable. Okay, so we have these two extremes. On one hand side, if you only ask for soundness, well, everything is monitorable, everything has a sound monitor, but that gives you very little guarantees on the behavior of your monitor. And in the other extreme, well, you can ask for sound and complete monitors, and you get very strong guarantees, but then on the other hand, you don't have any properties that are monitorable with those guarantees. So the space of interesting notions of monitorability lives in between these two extremes. So if we start by thinking about, well, what's the least we can ask for a monitor, for a sound monitor, to make it at least a somewhat useful object? Well, what makes the monitor useful is that, well, it should reach it should be able to reach a verdict. There should be some execution after which it reaches a verdict. So we can say that a monitor is informative if there is a trace that it accepts or that it rejects. So this is a kind of tiny bit more than soundness. We have a monitor, at least we know that it is able to give some useful information. And this already partitions our space of specifications into those that have informative monitors and into those that don't. So here's an example of a monitor that is informative. So it reads a beta and rejects. It's informative for our property always and forever alpha. However, not all properties have informative monitors. For example, eventually always beta, so beta occurs infinitely often, has no sound and informative monitor, since every prefix of this property, well, it's a property that depends on the infinite behavior. So whether beta occurs infinitely often, and then is no prefix that can definitely tell you whether all of its execution, all of its extensions will or will not satisfy this property. So already we get a non-trivial partitioning of the space of specifications into those that have this type of informative monitors and those that don't. And we can then describe this as informative monitorability. Okay, so we've added, we've looked at what's the kind of minimal requirement, the minimal guarantees a monitor can provide to make them interesting. We can also start from soundness and completeness and see how we can relax that to get a more interesting notion of monitorability. So if instead of asking for our monitor to be complete, both for violations and satisfactions, we can ask for half. So recall that our completeness required our monitor to identify both all violations and all satisfactions. But now we can say that a monitor is violation complete for a property if for all violations, so for all traces that are not in our specifications, our monitor can reject them. And here we don't care about traces that are in the property. So we might have monitors that never accept anything, but as long as they reject all of the traces that violate the property, we are happy, and that gives us violation complete monitors. Dually, of course, we can also define satisfaction complete monitors, which are the monitors that correctly identify all traces that satisfy our property. So this is somewhat weaker than the completeness we previously looked at, and allows us to again partition our set of specifications into those that have such violation complete monitors and those that don't. And this gives us another notion of monitorability that I'll call violation monitorability and satisfaction monitorability. To go look at a couple of examples. So here we have an alphabet of events with alphas and betas. Our monitor, if we have a monitor that can observe a beta and reject, and our specification is alpha to meet the omega, so alpha forever, and our trace has to be infinite, then, well, beta is not violation complete because, well, it will identify only the violations that start with a beta. But if beta is in the second or the third or some other position, this does not give us a violation. Our monitor does not reject, so it is not violation complete. Here we have a slightly more complicated monitor, which can observe alphas, as many alphas as it wants to, and when it observes a beta, it will reject. And again, if we look at the same property, now this monitor will identify many more violations, but it is still not violation complete because our specification does not include finite traces. So this is a monitor that can identify all traces that violate the property because a beta occurs, but it cannot identify that a trace is finite, and therefore it is not violation complete for this property. It is, however, violation complete for the property that only alphas occurs and a trace can be finite or infinite, because now all the violations have a beta that occurs, and this monitor can't identify all of those. So this is a violation complete monitor for this specification. Fourth example, I'll give you again maybe 30 seconds or so if you want to think, come up with a sound and violation complete monitor for the property acknowledgement only occurs immediately after a request. So here our specification does not say anything about whether the trace should be finite or should be infinite. We only care about the fact that acknowledgement should not occur in any other position than immediately after a request. And our alphabet has acknowledgements, requests, and awaits. So can we find a sound and violation complete monitor for this property? Well, yes, we can. Here is an example of one. It's probably not the only one. Here we have a monitor which rejects this acknowledgement immediately. It can process waits, and then if it sees a request, then it enters this second part of the monitor where seeing an acknowledgement does not reject, but brings us back to the start. And same, it brings, with the wait we come back, but with the request we will stay within the second part of the monitor that allows us to see acknowledgements. Okay, so you can think of this again as a kind of small automaton with this three-valued semantics, except here we only have rejects. Okay, so that's some violation complete monitors. And this gives us another level in this hierarchy. We can have monitors that are sound and then either violation or satisfaction complete. And finally, we can still find something in between our informative and our satisfaction or violation complete monitors. Recall that an informative monitor needs to be able to reach a verdict for some trace. And now we can make that invariant across the execution. And we can say that after reading any prefix, we should still be able to reach a verdict for some trace. And I'll call this persistently informative monitors. They are monitors which, after reading any trace, they should be still able to reach a verdict. Okay, so for example, eventually success or never failure is a specification that has a persistently informative monitor, because this eventually success part of the specification allows us to always accept if we see success. So whatever prefix of a trace you have seen so far, there is an extension which will allow you to give an accepting verdict, which is if you add a success. So we have that monitor that will wait for a success to occur, and that is persistently informative. On the other hand, not all specifications have such persistently informative monitors. For example, if we look at the specification, either end occurs before request or request is always eventually followed by acknowledgement. Well, we do have an informative monitor for this, namely if end occurs before a request, then we can stop our monitoring and we can say this execution satisfies our specification. However, if instead of reading end before request, if we see a request first, then the property will hold if and only if a request is always eventually followed by acknowledgement, and that we can't monitor informatively for. So this monitor has no persistently informative monitor. Okay.
Can I ask a question, Carolina?
Yeah, of course.
In the first one of the two that you have got, supposing instead of disjunction, I put a conjunction, right? Eventually success and never fail. Then also I have a persistently informative monitor, right?
So if I have eventually success and never fail, then...
What I mean is,
so then because of the never fail component, you will have a persistently informative monitor, yes, because you can also always add a fail.
But then will one have an informative monitoring as well? I mean, monitor as well, not persistent, but just. You understand, right? I mean.
Yes, you would have an informative monitor because the one that would reject after seeing failure. If you have an unconsiderable one.
Yeah. No, so I'm trying to think of. Okay, sorry. I'm trying to think of something which is persistently monitorable, but not, persistently informatively monitorable or whatever, but not informatively monitorable.
So there is an implication. So all persistently informative monitors are also informative, since, yeah.
I see. Okay.
Right, because if if a monitor is persistently informative, then in particular it can reach a verdict, which makes it also informative. So there's an implication. So this hierarchy that we are building, there is an implications going all the way in one direction. So anything that has sound and complete, if a monitor is sound and complete, then it is in particular, either it is violation complete and it is satisfaction complete. Any monitor that is satisfaction complete or violation complete is also persistently informative. And any monitor that is persistently informative is in particular informative, and of course every monitor is sound. So this is indeed a hierarchy in the, there is a strict inclusion going on in between all of these different notions of monitorability.
And what would be an example of something that does not have an informative monitor?
For example, request is always eventually followed by an acknowledgement, has no informative monitor. Or even simpler than that, saying that request occurs infinitely often. Because we are talking about the infinite, the only thing that matters for this specification is what happens in the limit. Whether something occurs infinitely often or not, there is no finite prefix that can tell us anything about it. So we have no informative monitor there.
Thank you.
Okay, so then, so these are properties of monitors. We're saying that a monitor for a specification can have one of these different levels of guarantees. And then we can use this to define what properties are monitorable for. By saying a property is soundly monitorable or informatively monitorable, persistently informatively monitorable, if it has a monitor that is sound and persistently informative. Specification is violation monitorable if it has a sound and violation complete monitor. And this gives us this hierarchy among specifications that tells us what kind of guarantees we can expect from a monitor. And now, so this is a kind of very abstract hierarchy, but it is grounded in in the setting that we've built. So what I mean by that is that recall that I've said that only the properties true and false have a sound and complete monitor. But this is only the case if we're in the domain where we have both finite and infinite traces. And this changes if we change the domain. So if we now say that I am confident that all executions are infinite, then more things have sound and complete monitors. So then all properties, all bounded properties have sound and complete monitors. And now bounded properties are properties that can be determined from a prefix of bounded length. So for example, the property, the third event is alpha. This is a bounded property because the prefixes of length alpha, I can just look at the 3 first events, and this will tell me whether my execution satisfies this specification or not. So these are bounded properties. You can characterize them syntactically in whatever your favorite formalism is. And this is a set of properties which, if we are only on infinite traces, will have sound and complete monitors. But if we also have finite traces, then they don't. So the domain matters a lot. And in particular, looking at the domain allows us to include prior knowledge into our monitors. So if we know that our executions, they come from a system that satisfies some properties, some independence properties, if we know something about the system, then we can restrict the traces that we have these requirements of soundness and completeness for. We can restrict those to the set of traces that we are interested in, and this will make more properties monitorable. So this will change how monitorable properties are. For example, if we know that our traces are infinite, then we have more sound and complete, soundly and completely monitorable specifications. So this is one of the parameters that will affect what is monitorable. Another important parameter is how we define our monitors. So as the monitors we've been playing with, they are finite state, but you might decide that actually you want your monitor to have a stack. And now if your specification is that the number of closing brackets is always smaller or equal to the number of opening brackets, then you will be very happy to have a stack, since this property has a violation complete monitor if you consider monitors that have a stack. But it doesn't have a violation complete monitor if you just look at the finite space monitors that I showed you. So the monitor model is, of course, a parameter of monitorability. And here, if you, depending what types of specifications you're interested in, at some point you will run into issues of completability. If you increase the complexity of your specifications too much, then maybe Turing machines are just not going to be enough for monitoring them. And now, of course, runtime verification is meant to be a kind of cheap and cheerful, low overhead exercise. So if you start running into computability issues, the practitioners might start raising their eyebrows. But it's still something to keep in mind. The resources you are using to build your monitors will also dictate what specifications are monitorable. So then if we go back to this question of what specifications are monitorable, well, we have all the ingredients we need to be able to answer this. Namely, you pick your favorite monitor model, whether that's finite state monitors, monitors with registers, with clocks, or whatever other model of computation you want to work with. You choose your domain, you think about whatever assumptions or prior knowledge you have about your setting, how you can include that in your domain. And from this, you can define this monitorability hierarchy that is a partition of the specifications into those that have these different monitors that can provide you with different strengths of guarantees at runtime. Now, so the way I've defined monitorability here is by starting with the monitors and looking at what are the guarantees that I can get from those monitors. But you can also define monitorability denotationally, or what would be a more denotational as opposed to operational approach, by looking at some good and bad and ugly prefixes. So these appear a lot in monitorability literature, very classic definitions. We say that a good prefix is a prefix that only has extensions in the specification. So these are the prefixes which, once a monitor has seen that prefix, it can safely say, yes, I am happy with this, I will accept this choice. The dual bad prefixes are those which only have extensions that are not in my specification. Again, these are the prefixes which a monitor can see and happily reject. And now an ugly prefix is one that has no good or bad extension. So these are the prefixes after which my monitor can give up because it knows that it can no longer reach a prefix that determines the property. And we can use these notions of good, bad, and ugly prefix. Let's first look at an example. So, for example, here we have a property, I believe we might have seen it before. Either end occurs before a request, or request is always eventually followed by acknowledge. Well, this has a good prefix, namely all prefixes where end occurs before a request, they are good, because then my monitor can stop and I am happy. But it also has ugly prefixes, namely, if I see a request before end, then I have a prefix which has no good nor bad extension, because then whether the property is satisfied depends on this second part. And now we can use these definitions of good, bad, and ugly prefixes to get back our definitions of monitorability. So we can say that we can come back to our definition of informative monitorability by saying that a specification is informatively monitorable if and only if it has either a good prefix or a bad prefix. So this corresponds to my monitor can do something useful. We can get our definition of persistently informative monitorability as the set of specifications that have no ugly prefix. And this is one of the kind of classic definitions you will find throughout the literature, used in particular by Bauer-Leuke and Charlotte, and it's often attributed to Pnelli and Sachs, although I believe Pnelli and Sachs never actually used this definition. They did. They had slightly different definition going on. But anyway, this is one of the classics that you'll find in the literature, this no ugly prefix definition. And it corresponds exactly to this operational version we saw earlier. And finally, if every violation of our property has a bad prefix, this corresponds to our violation monitorability and also to the class of safety properties, which you'll also see throughout the literature. So this is kind of a different approach to building these definitions of monitorability. And what's interesting in about this difference is that you can, they don't talk about monitors at all. So you can just look at a property and look at its prefixes and say something about its monitorability, which is completely independent of the monitor model. And in contrast, the operational approach takes the monitor explicitly. It starts with the monitor, considers how its computational power, and looks at the guarantees that it can provide. And it kind of makes all of these things explicit. And what's nice about that is that, well, then if you change the parameters of your monitor, it's clear how that affects the specifications that are monitorable. But as we see, these two approaches, they do end up with the same notions of monitorability. So maybe I'll have a couple of minutes, so I'll just go a couple of examples of how we classify these properties. So we have eventually success and never failure. So this was also, I think, one of the properties we mentioned. Well, what is how monitorable is this property? Well, we can't monitor for satisfactions because we have this and, so eventually seeing a success is not going to be enough. However, we can monitor for violations, because if failure occurs, then we know that the whole property is violated. So this first property will admit violation complete monitor and is violation monitorable. Oh, right. No, so it is not violation complete because we can also fail it by never seeing success, and that is not monitorable. So here it is persistently, informatively monitorable. This happens when you don't put in the answers into your slides. Every other event is an acknowledgement. Well, here we can monitor all of the failures, so this would be violation complete. The third event is open. We saw that this is completely monitorable if we are only on infinite traces, but if we have both finite and infinite traces, then we cannot monitor it completely, because in particular, if we have a very short trace where we only have 2 events, then that is a failure that we cannot monitor for. On the other hand, we can monitor for all of the satisfactions, namely by seeing the third event being open. The execution is infinite. Well, since our monitors cannot tell whether an execution is over, we cannot monitor for the violations nor the satisfactions of this property. And finally, request is always immediately followed by acknowledgement. Well, here we do get a violation complete monitor, but we don't get a satisfaction complete monitor. Before the end, I still want to mention, well, so we've talked a lot about the theory of what makes a property monitorable. So now you may ask, well, how does that help me? I want to do some runtime verification. I have some specifications. You've just spent an hour telling me about whether this is monitorable, what kind of monitorable is it? How does that actually help me build a monitor for this property? And so this is the problem of monitor synthesis, where you take a specification and you would like to output a monitor that does something relevant. And now I'd argue that directly, all of these things we've talked about monitorability do not help you in this problem directly, but it does help you define this problem. Namely, since you are interested in outputting a monitor that is somehow related to your specification, the definition of monitorability is going to tell you what's your notion of correctness for your output. So what do you expect from your monitor? So understanding the different notions of monitorability you can use will tell you whether the monitors you output, whether they actually satisfy the guarantees that you expect. And understanding these notions of monitorability also then allows you to say, once you output a monitor, to say, this is a monitor that is violation complete. This means that whenever there is a violation of my property, my monitor will be able to identify it. And this is a very reassuring thing to know if you are inputting the output of an unknown component into your critical system. Even if you don't have a guarantee that the unknown component is correct, having the guarantee that, well, if it fails, I will be aware that it fails. That is a useful guarantee to have. On the other hand, if you have the guarantee that whenever the system does not fail, so whenever the execution is a good one, then your monitor will identify it. So if you have a satisfaction complete monitor, that is a very different guarantee you have, and you're going to use that kind of a monitor in a very different way than the one that flags all of the violations. So I'd argue that it's good to know what the guarantees of your monitors have, even if today I'm not going to have time to go into detail about how you actually synthesize monitors. So a quick recap: we've seen that the notion of correctness for a monitor is not entirely straightforward. You definitely want soundness, but then you also probably want some level of completeness. And there are different things that you might ask, but what you get will depend on what your specifications are. And that is where monitorability comes in, the different notions, different levels of monitorability. And we can put those into this neat hierarchy that partitions our specifications. And we've seen that the parameters that affect those are, in particular, the domain and the prior knowledge that we have about our system and the computational power of our monitors. And as I said, we've kind of done this through an operational approach that makes these parameters very explicit, which means that then we can have these explicit guarantees about what happens at runtime. I'll leave you with a bit of the kind of recent literature on these things. So an operational guide to monitorability with Aceto, Luca, Antonis, Adrian and Anna, that kind of recaps these levels of the monitorability hierarchy that I've shown you. And in particular, what it does, it also gives you syntactic characterizations. So it tells you what logic you can express these different levels with. And you'll find that some of these levels of monitorability have very straightforward syntactic characterizations, while something like persistently informative monitorability, you get actually a kind of complicated fragment. That also tells you about kind of how natural some of these notions might be. The Popple 2019 paper, that goes more into details about synthesis, which I have completely skipped for this talk, so that's a good place to look. Then these two papers, both the CSL paper and Henziger and Sarek's runtime verification paper this year, they deal with about how to integrate prior knowledge into your monitors. I think that's my time, so I'll leave it at that. Thank you very much for your attention.
Thank you very much, Carolina. And yeah, well, we are a little over time, but then we have a long break coming, so people should be happy to ask questions.
So can I go ahead? I have
yes, please. Yes.
Yeah. So maybe it's a stupid question. So if we ensure that the system indicates when it terminates, would some of this finite, infinite thing go away, or?
Yes. So if you have an end of trace marker, then suddenly you can monitor everything because, so assuming if all traces terminate and you have an end of trace marker, then everything is monitorable because your monitor can just wait for the end of trace marker and then analyze the whole execution and just do a kind of check whether
but there are still non-terminating executions, right? So
so if you say not all executions terminate, but you know when it terminates,
exactly.
Yeah, so then you'd probably end up being in a situation that's quite. So yeah, so that definitely will affect things, and then not everything will be again monitorable because you'll have infinite traces. You will get more things that are monitorable. For example, again, the bounded properties will become monitorable because you don't have to worry about the trace ending. So I think you'll probably end up with a situation that's very similar or identical, I'm not sure, to if you're only on infinite traces. You probably, yeah, it might even be exactly identical if you have an end of trace marker.
Okay. Thank you.
That's a good question.
I have a question. Can I ask it now?
Yeah, please.
If you fix the specifications, for instance, like LTL or mu calculus, is it then easy to decide if a specification is one of these monitorability criteria?
So that's a very nice question. So for the mu calculus, we can recognize at least safety properties in the mu calculus, so that is decidable. For persistently informative monitorability, that's a bit less trivial because there the fragment of the mu calculus that you would be looking at is quite strange as a fragment. So it's not completely clear to me how decidable that is. I would guess it is decidable. Now for LTL, yeah, so LTL, if you're just looking at monitorability, you would just translate it into the mu calculus and you're happy. Yeah. So I think for the mu calculus, I would guess that it's all decidable. But at least for the persistently informative fragment, which is a bit of a strange one, I'm not completely sure.
Yeah, thank you.
Other questions? I had a couple of questions. One is related to what Kumar was asking. In the case of when you have only infinite sequences, is it the case that more properties become monitorable? I mean, it looks like that to me, at least with a couple of examples, but what happens in the hierarchy? Look at a comparison.
Yeah, so the main difference is that you get this complete, you have this complete class of completely monitorable properties becomes bigger. For the other, if I recall correctly, the other classes, they don't change drastically. Again, the persistently informative is the tricky one. I have to check, but yeah, I think the main difference is the complete monitorability that changes.
And are there some clear closure properties for monitorability that,
So,
I mean,
yeah,
your characterization suggests something, but
yeah. Yeah, so again, some of the classes will have better, well, depending on the class. So things like safety properties, you have closure under one Boolean combination, but not the other. So here again, it depends on whether we are only on finite and infinite or infinite. So if we have also finite traces, then you have worse closure properties. So I think then, say for safety, you don't have closure on the union, if I recall correctly, while if you're only on the infinite, then you have slightly better closure properties. While again, persistently informative monitorability, their closure properties become much trickier. But yeah, so there's not always closed under Boolean combinations.
But is there some work on characterizations of this kind that you can do?
So if you look at this, these syntactic characterizations,
that's right.
Then from there you can, I think from there, at least the kind of Boolean closure properties become easier to see because then you're looking at those syntax, so whether that syntax has those characteristics.
Okay. Thank you. Are there other questions? Okay. Okay, then. Thanks very much, Carolina.
Thank you for having me and for organizing this workshop.
Thank you. I think we have a long break now, and we will get back in an hour and 20 minutes. It's 5:30 Indian time. Thank you. Thank you.
Hi, Joshua. Are you telling something? Or, hi.
I think he wanted you to make his second account also a host, which
yes,
is going to project.
Laptop, and I want to share the screen. Yeah. But I will be talking through this one.
Let me see if I can do it. Am I? Give me a minute. Maybe I'm not in the right.
Yeah, I'm sorry to make it so complicated. I don't have an iPad, but I do have this Microsoft Surface.
No, I think. Give me a minute. I think I should be able to do this. Just
yes. Excellent. Let's see.
Doesn't look like. You are a co-host. Okay.
Sorry?
Yeah. Sorry. Yeah. Yeah, unfortunately, I think the part that you have struck out, it should have been Goa, India, but yeah, it is online.
It's okay. Seems to work. Yeah, but to be honest, so we have a baby at home, so it would not be easy for me to actually go to India.
This is true, but Goa is a nice place. I mean, sometime you should visit if you get a chance, I think.
Hi, Prakash. Shall we start?
Yeah, I think we can start. Yeah.
Okay, so welcome to the third talk in this workshop in advances in verification. It's a pleasure to invite Joshua Merman, who is a postdoc currently at Aachen, working on probabilistic programs, but his PhD in Radboud University was on nominal automata and black box testing in the context of active automata learning. So what he's going to be talking about today is recent applications and advances of automata learning. Over to you, Joshua.
Hello, thanks for the invitation. I will be happy to talk about automata learning. So this week we had a bit of a strong lockdown in Germany, so I could not attend the rest of the conference, but I looked at the program and I think you had a very nice week so far. I hope that you can enjoy this last, well, for you evening, for us in Europe, it's the afternoon. Perhaps people in America, it's morning. So yeah, automata learning. So I will talk about this, and it has many other names perhaps. So maybe you know this as system identification or state fuzzing, regular extrapolation, grammatical inference, regular inference, or model learning. So these are all kind of the same name for the same, or a different name for the same kind of technique, maybe a bit more general, but it's applied in a kind of a wide context in computer science. So to give you an idea of the problem, let's consider this this bank card reader, and we want to verify the reader. So I made a mistake. We want to verify the reader, and we want to check whether it behaves as we expect it to. Now this is a problem because we may not have all the source code for this little device, because maybe we have third-party libraries or some components were offshore developed, or we have to rely on the chip. And of course, this chip itself is manufactured by a different company, so we cannot really know what's happening inside. We may have a model for this hardware, but maybe it's not correct because maybe something has changed or it's not up to date. So all in all, we could try to do model checking or static analysis, but on the actual device, we cannot do this because we simply do not have all the ingredients to do that. So how would we verify the actual device when we want to know whether it's correct? And one technique which has been proposed is that of automata learning. So here we see the same device, it's here. And so researchers here have built some Lego around it in order to automatically push buttons on this device. And by doing so, you can make observations. And from these observations, you can actually infer a state machine. And once you have the state machine, you can do, for example, model checking. So this is the high-level idea and the high-level problem we are going to solve with automata learning. So we want to make observations on some kind of device or software or anything. From these observations, we make a model, and then the door is open for verification. And in this case, this bank card reader was flawed. So this is a Dutch news article. It says that the e-banking from this bank, it's vulnerable. And then later it has been fixed. And then with the same technique, you could learn a second state machine for this new version, and they could show that indeed the bug was fixed. So that's quite nice. Okay, so the outline of this tutorial is as follows. I will start with the basic learning algorithm. I do this because I think it's nice to see that it's not magic what's happening behind the scenes. This algorithm for inferring a state machine from observations is really quite simple. And then afterwards, I will discuss, of course, more recent advances, such as applications, and also extensions to other types of automata. Okay, of course, when you have any question, please interrupt. I like this to be interactive, so you can just interrupt me at any time. Okay, so let's start with the basic learning algorithm. So for now, I fixed this alphabet, just 2 letters A and B, and there's some language L. So it's a subset of all the words. Another way to think about a language, and I will often do this, is to think of it as a function from words to the Booleans. Okay, it's the same thing, of course, just represented differently. But this is sometimes easier to think about it as a function. And let's try to do this learning top down. So let's suppose we already know the language. How can we then construct an automaton accepting exactly this language L? And for this, I'm going to introduce a very big matrix. It's a very redundant structure, but from this, we hope to see the automaton. So here's the big matrix. So what I do here is I have rows. For each word, I have a row where this is the empty word. And also for each column, I will have, I put all the words. And these are called the prefixes and these are called the suffixes. And if you combine them, you put a 1 in this cell in the matrix precisely if this is a word in the language. So in this example, we have a fixed language here. AAB is accepted, but for example, AAA is rejected. So we make this very big matrix. Can someone guess perhaps which language is used here? Just to see whether you are all connected.
Words ending in a B.
Perhaps it's easy.
Oh, no.
Say it again.
Okay, I thought words ending in a B, but that's not correct.
I mean, it's close, right? So we indeed see if it ends with a B, there's many things accepted here. Whereas if it ends with an A, then nothing gets accepted. So it's not too bad. Someone else may dare a second guess?
Ends in AB.
Say it again.
Words ending in AB.
Words ending in AB. Well, let's see. So here we have the word B, AB, and it's rejected. So it's not quite that. But you're getting close.
So
I will
beginning
just
in an A and
it.
ending in a B.
Yes, exactly. Yes, you have it. So this matrix is called the Henkel matrix. And in this particular case, the language I chose was all the words starting with A, ending with B. And this is an infinite structure. Okay, so what can we do with this structure? So let's consider 2 rows. And these 2 rows have different entries in these cells. So for example, here there's a 1, whereas here is a 0. So these rows are different. This means that if we have some automaton for this language, then after having read this word and after having read this word, the automaton has to be in different states. Because from these particular states, the behavior on the word B is different. Okay? So at least we now know there's at least 2 states based on this idea. If we color all the similar rows with the same color, so we just consider this row here with all the same rows, we also color yellow. And we just consider this blue one here and the same one we also consider color blue. Then we can see that all the blue rows will represent the same state. They have the same behavior because on every suffix, they will either accept or reject in the same way. So we can already see that, well, for these rows, we only need 2 states. Well, in this matrix, we have 4 colors in total. There's 4 different types of rows we can see. And in fact, there's a theorem. Oh, sorry. Yeah, so we can say 2 rows are similar if they have the same color, meaning that they have the same entries in this matrix. And there's the theorem, which is normally attributed to Myhill-Nerode, but actually Schuchen-Berger proved it earlier. A language is regular if and only if this matrix contains a finite number of colors, if and only if it is accepted by a finite automaton. So let's try to reconstruct the automaton from this matrix. So we have 4 colors, so we need 4 states. So let's draw them. And let's say this is the initial state, which is then represented by this red row on top. So this red row, it goes to with the A transition, it has to go to blue. So let's draw this. And with B, it goes here. to yellow. Neither of these three states is accepting. We know this because the behavior on the empty word is reject. So it doesn't do anything yet. Okay, but then from the blue, so this was blue. What happens there? Well, we can do another A transition, and then we remain in the blue state. Or we do a B transition, and then we come to the orange state. So this is orange. This is yellow. This was red. Okay, let's do the yellow state now. So this B. If we do an A transition, we remain in yellow, and also when we do a B transition, we remain in yellow. So this will be a self loop with A and B. And the orange state, well, let's see, we have A, B. If we then do an A transition, we should have ABA, which is it's not in the matrix, unfortunately. But it will go back to the blue state, and the B will remain here. And this is the only one where the empty word is accepted. So this has to be an accepting state. I hope you can kind of see the automaton. I try to kind of have the matrix and the automaton in the same picture here. But what we did here is that we looked at this matrix. We looked at which rows are the same. Those have to be states. Successor states can then be obtained by just appending a single letter to the previous state. So here we have the empty word, and then you move to A with an A transition. But also when you had A here, we move to AA with the A transition. So we simply append to these words which represent states. And also the acceptance was, we could read off from the first column, and the initial state was defined by the first row, which is indexed by the empty word. So this is the syntactic automaton constructed from this matrix. And this is exactly also a minimal automaton. It's the smallest one you get. Okay. So that's how you construct an automaton from this infinite matrix. So this assumes that we know everything from L. But how can we do this when we only know little bits of L? Because remember, we want to learn the automaton, so we don't know L yet. We only know maybe little pieces of L. And then one observation is that in this whole matrix, there's only a few things you really need in order to reconstruct the automaton. And it's, you need 3 columns. So you need the empty word column, the one with the B and the one with AB in this example. And we needed 4 rows. Well, of course, we need 4 rows because there's 4 states. There's 4 different colors. And we need the columns in order to distinguish those rows. So we see that this and here separates this row from the other 3. And then this column here separates this row indexed by A from these other 2. And then what remains to separate is this row here from this row, and we need AB for that. So once you have this finite part of the table, you can actually reconstruct the automaton. So this is maybe something you don't know. So the mile road is, of course, a very classical theorem. But the fact that you have this finite kind of, you only define many rows and find many columns is kind of an extra like detail to the theorem you can think of. Okay, so at least there is some finite part of this whole matrix which we can use to reconstruct the automaton. Okay, so how would you learn an automaton for an unknown language? So the algorithm I will describe, and I will also give an example of, is called L-star. It's by Dana Englund from the 80s in the paper Learning Regular Sets from Queries and Counterexamples. So the algorithm is as follows, roughly. So we start with the smallest possible table, just the empty word as a row and the empty word as a column. And then we keep extending the table until it is so-called closed and consistent. I will define in a moment what those things mean. If it is closed and consistent, we construct an automaton, and then we check whether it's the right automaton for the language we want to learn. If it's wrong, then we have to refine and then repeat this process. If it is correct, then of course we are done with learning. So this is the sketch of the algorithm. And I will now explain what closed and consistent means. Okay, so here's this the same table as before. This finite part of the whole matrix, the finite part we needed. There's one thing we also need is, in order to talk about transitions, we have to know kind of the one-letter extensions of these rows. So we need this kind of bottom part of the table. So what I've done here is, well, for every row here, I extended it with A and B, and then I got these rows. So for example, this row already extends into the top part. It's already there, so we don't have to add this. But then for A, we need to add AA in the bottom part, and AB is already there. So we just need to also keep track of these observations in order to make the transitions. Okay, so a table is closed if for each extension, so for each of the things bottom in the bottom part, there is a row with the same color in the top part. In this example, it is closed. For example, this extension here is yellow, and yellow already appears here. Or more technically, perhaps you could say, well, the row is 0, 0, 0, and this already appears in the top part. Okay. And you can check for every extension that this holds. So this ensures that some transition is enabled for all the states represented by the top part. The second notion is that of consistency. And we will see this perhaps better in the example, but what we want is that these transitions, they are also well defined. So for rows with the same color, the extensions should also have the same color. And this is exactly what consistency means. Similar rows in the top part have similar extensions. Now in this case, all the rows in the top part have a different color, so it's consistent trivially. But we could imagine that perhaps this row was also in the top part for some reason, so the row BA. Then what we would like to have is that BA and BAA have the same color, and BB and BAB will have the same color. And we will later see that this is the case in this example. Okay, so what's the deal with closed and consistent? It's exactly these properties which allow us to construct a well-defined automaton from this table. So as soon as we get a table big enough which is closed and consistent, we can construct an automaton. And this automaton also accepts and rejects all the words exactly as we see in the table. So if the table says, well, something has to be accepted, this automaton will do so. There's a bit more. If it is not closed, then it means that some row in the bottom part has a different color. And it means that this row has to be added to the top part. And the same for consistency. If it's not consistent, then we know a column which has to be added to the table. And so this way we can extend the table. Okay, there's one more thing I have to discuss. How do we know the values in these cells? So I've been talking about extending the table and with closeness and consistency, but how do we actually get these values? For example, how do we know the value here for BB? And for this, Dana Engluin introduced the concept of a learner, teacher, and queries. So you can think of it as follows. There's someone, the learner, who wants to know a language, and there's a teacher who is helping him to learn it. And the learner can maybe ask, well, is this a word or is this not a word? So the learner is allowed to ask membership queries. So the learner can ask, is W in L? And then the teacher has to respond with yes or no. So in this picture, it's my son asking me whether something is a word or not. In practice, in verification, what we have is the teacher is the device itself. And the learner is everything around it. It's like the algorithm which we run on the computer, and in this case, the Lego pushing the buttons. And so what happens is that if you want to know whether a certain word is in the language, we simply send this word to the device. We perform these actions in the word, and then we observe what this device tells us. So the device may give an error code, or may make a beep, or maybe does something else, and we can observe this. And so in general, the response doesn't have to be yes or no. It can be any kind of output which we can observe. And we can just put this to the table. So in general, we can learn Mealy machines or Moore machines, not just DFAs. And so this is the setup which we use. And so we can fill the table with any kind of word we like. So I would like to say this is a bit different than this monitoring, which we saw earlier today. Is in monitoring, the system is running and you're just observing. In learning, we are actively learning. So the learner, so the algorithm, can decide on which words it wants to know what happens. And then it will do so. It will perform these words, and then it will also reset the machine and then perform the next word. So it's different than monitoring, because we are now in control of the device. Okay, so this way we can fill the table. If you remember in the sketch of the algorithm, there was one last step is check equivalence. And this we also delegate to the teacher. So the learner is also allowed to ask, is my automaton correct? And we will later see how to do this, but this is a nice thing to abstract away from, because then the learner can really focus on getting the table right, constructing the right automaton, and then how we implement this equivalence, someone else can decide. Like, we can do this in various ways. One catch here is that if it's not correct, the teacher will have to provide a counterexample. It will have to say, well, on this word, the hypothesis A, so A will be called a hypothesis, it is wrong. Okay? And then based on this, you can extend the table and you can refine and continue learning. Okay, so now let's do this example. So we have this language, we already know it now. It's all the words starting with A, ending in B. But let's just run the whole algorithm on this example. So we start with the empty words. And the empty word is not accepted, so we put a 0. So this is the top part. And we need to know about the one-letter exception. So we have to know about A and B. Those are also not accepted. So now we check closeness. Is this closed? Well, both these rows appear in the top part. It's just a single 0, it's there, so it's closed. And it's also consistent because there's only one row in the top part, so there are no similar rows. So it's closed and consistent. We can make a well-defined automaton. And it's a trivial one. So it's a single state with a self loop, and nothing gets accepted. So this is the first hypothesis of the learner. And now the learner can ask, well, is this correct? And the teacher will say, well, no, because there's a counterexample, AB. AB is a word which is in the language, but it's not accepted by your automaton. So what the L-star algorithm I have to move things around a bit. So these will be the rows in the top part. And we still have the B in the lower part. And we will also have the ABA in the lower part and the AB. Well, we first have perhaps AA, AB, and then ABA, AB. Those are the extensions of the things in the top part. So AB is accepted, of course. Okay. Well, this one was not accepted. We already knew that. AA is not accepted. AB is accepted. Oh, it's already there. Sorry. Let me move around things. ABA is not accepted. ABB is accepted. Okay. So after adding the counterexample as a row, this is a new table. So it is still closed. So all these things here, they appear in the top part. So it is closed. But now it's not consistent anymore. These two rows are similar. There's a 0, and in this case, there's also a 0. But if you now extend with a B, so we extend a B, then we get this row from the empty word, and we get a B from the A word. And these two So these were similar, these are not similar. Okay. So this is an inconsistency. So what do we have to do is we have to add a column. And in this case, it's the letter B, which we have to add as a column. And of course, skipping some details on why this is the one we have to add, but just let's add it. And then let's fill in these cells. So just a single B is not accepted, and AB is accepted, ABB is also accepted. This one is not, this one is, and this one is. Okay, so now we see that we have fixed the inconsistency because previously these were similar, but now they are different. So what happens here is that the algorithm has learned that the states represented by these words have to be different. They have different behavior, namely on a B, they perform different. So they have to be two different states. They cannot be the same state. Okay. Now let's check, is it still closed? So we added something, so we have to check whether it's closed again. And we see that every row here appears in the top part. So there's now 3 colors. There's the 0, 0 here, which appears there. There's the 0, 1, and there's the 1, 1. All of them appear in the top part. So it is closed, and this again, it's consistent. So we make a second hypothesis. So in this case, we need 3 states. We do this as before when we knew the whole matrix. The first row will be the initial state. And well, we have the A and we have a B. And this one is accepting. And so one thing which is interesting is the B transition from the first state goes to a row which is 0. From the A state, this one, when we make an A transition, we come into a row with 0, 1, which is the same state as we came from. And from the AB state, so from this state, as a 1, 1 row, we see we can either go to the previous state with an A, or we remain in the same state with the B. Okay. So far, this is what the learner has done. It added a row, a column in order to fix consistency, and then it was able to do a second hypothesis. So now the question is this correct? So this is now the automaton. Is this the correct automaton? Does someone want to answer this question?
Well, no, because you can accept BAB, for example.
Exactly. So a counterexample would be BAB, which is accepted by the automaton, but it's not in the language we want to learn. So then we do the same thing again. So we add B and BA and BAB as rows in the table. And in particular, what happens is that, so in particular, B is added to the top part, right? So this will be a new row, and it will also have some extensions here. And what will happen, I will not do this in detail, what will happen is that these two are similar, but one of the extensions is not similar. And what will happen is that there has to be a new column, AB, which then differentiates this row from this row. And once that has been done, we see we need 4 states, and then we actually get the exact automaton for this language. But I will not do this in detail. Right. Okay, so any questions so far? Like, is this algorithm more or less clear? So we can make observations to the thing we want to learn just by performing these actions. We see what happens. We fill the table, and we just keep filling and extending rows and columns until we make some hypothesis. And then, well, I will explain in a moment how we do the equivalence queries, but then with the help of equivalence queries, we can either accept, like we get the right thing, or we get something wrong, and then we can refine. And then this loops until we're done. So yeah, so one thing I should mention here and on this slide is that this algorithm will actually terminate. So for a regular language L, it will always terminate. And it will even do so in polynomially many steps. Now, what's the input to this algorithm? It's a bit unclear. So it is polynomial in the target, which we are learning. So of course, this is something we are constructing on the fly by doing queries. And only in the end, we know how big it is, right? So we don't know in advance how long it will take. But if you know the target, then you can say how long it takes. And also it depends on these counterexamples we get, because the teacher may be maybe unfriendly and give you a very, very long word on which you do wrong. And of course, you have to read this word. So we have to take into account the length of the counterexample as well when we discuss complexity here. So nowadays there's more efficient algorithms. I think the most efficient one nowadays is TTT. It's by Malte Isberner from Dortmund and his group back then. And well, there's a long history of all kinds of improvements and variations on L star. And here you can see a summary of all the complexities and so on. Yeah. So what about the equivalence query? So far we have assumed that the teacher will just help you and say, well, yes, the automaton is right or it's wrong, and this is why. So in practice, what we do is we just do random testing. And this may seem a bit strange, like we try to be very exact, and we have this membership query and we try to be exact on everything. So why do we do this randomly? Well, not everything is lost. There's actually a strong theorem here. So we can show that if we do random testing, then for every epsilon and delta, with a high probability, we get a hypothesis which is very close to the target. We can show this. And so this is called a probably approximately correct algorithm. And it's actually also efficient in epsilon and delta. So you might think that random testing is a bit stupid, but it actually is the right thing to do. It's efficient, and it actually gets a pretty strong result. And of course, it will always be an incomplete technique if you don't know exactly the device you're learning, because there might be some hidden thing. There might be a password which you have to guess, and this is of course very hard. So it will be an incomplete technique, but at least we get probabilistic bounds. Okay. So this was the basic algorithm. Are there any questions so far?
So in one of the slides, you showed symbol complexity. What is that symbol complexity? Like I think in the related results.
So the query complexity is simply the number of membership queries. And normally you would also count the number of equivalence queries, but I don't think he did this in this table. But I think in all these algorithms, the number of equivalence queries is the order of n, so the size of the automaton. The symbol complexity is it's not just the number of queries, it's also the length of the queries. So it's really, how do you say, it's the sum of the length of all the queries. Does it make sense?
Okay, okay. Okay, and another quick question. So this seems to have a close connection with the minimality, right? So the minimality is somehow very important. But what about, like, so you were saying that there can be other classes which you can learn, for example, the Milli machine and the Moore machines. What if for some class of, automaton, such a Myhill-Nerode characterization is not known to exist? Can you still learn?
The answer is yes, but not perhaps efficiently. So one thing you can do, if you have equivalence queries, you can just enumerate all automata or all whatever you want to learn, you enumerate them, and just for everyone you ask an equivalence query. This is of course very inefficient, but it does fit the theoretical framework here. So the answer is yes, you can always learn in principle, but that's kind of guessing, right? That's just a brute force way of learning. What the Myhill-Roth theorem really helps is that it gives you a canonical way to construct the automaton.
Okay. Okay.
So it's not necessarily needed, perhaps, but it's, I think in most types of this kind of learning, we do rely on it. And so in the end, I will talk, for example, about register automata. And there we have almost a Myhill-Roth theorem. And that's good for learning.
Okay. Yeah. Okay, thank you.
Yeah, good questions. Okay, I will continue. Okay, so I will now describe some of the applications. So these are, I just tried to Google some applications, and I mean, some of the authors I know, but not all of them. I will just try to give a, well, it's not an overview, it's just some selected examples of applications. So one thing I know quite well is one of my colleagues at the Radboud University. They learned the TCP. So the TCP is a protocol for the internet, of course. It's used everywhere, basically. And they used different implementations for the TCP, well, both the server and the client. And so here they say they do this on Linux, on Windows, and FreeBSD. Now, of course, for Linux, you have the source code, and you could do static analysis, and you can do verification there. But Windows, at least for us, it's closed source. Of course, at Windows, they can do this, but as researchers, we cannot. But with learning, you can. So they can learn a state machine for the Windows implementation of TCP stack. And well, they did this, and then they applied model checking. So they obtained the state machines, they applied model checking, they formalized some of the TCP standard specification into LTL, and then they just checked. And what they note is that they do not conform to the specification. So there are bugs. And sometimes it's very small, as we will see in one of the things here. Yeah, so they had to extend the L-star algorithm here. It doesn't work out of the box. So what they did is they have to deal with data. I will explain in a second what exactly. And in order to do that, they used abstractions in the input alphabet. So let me explain this. So in TCP, you have these packets, which, I mean, I'm not an expert on this, but roughly it's like this. And the first field can be an acknowledgement or a synchronize or some other things. And then you have a sequence number, say N. And this is a 32-bit integer. And then you get the payload. Now the protocol depends on this sequence number. But of course, if you take the alphabet to be all 32-bit integers, it's way too big. You cannot learn way this specific number, N, but they say, well, it's some number, and then they have to keep track of which numbers are used. And then when they communicate with TCP server, they kind of, on the fly, they insert the right number or a different one, just to see what happens. So there will be the learner. So this is then, for example, L star. It sends an abstract query. For example, it says sends an acknowledgement with, well, I don't know how you would write this, but symbolic, maybe just with some number. Then there's something in between the learner and the teacher. So here's actually TCP, which they call it's a mapper. And it converts these symbolic inputs to actual inputs. So this will then be an acknowledgement on whatever sequence number it was. And then when you get something back, you have to retranslate backwards and pass it on. Okay, so this is kind of a technique they use. So they reduce the size of the input alphabet by abstraction, and they put something in between which keeps track of the sequence numbers which are needed. And by doing so, they were able to learn this state machine. This is the Windows implementation. And here, all the way on the bottom, there's something which is not conform to the specification. So I think in this case, it's not a vulnerability because it's in the close command, and it actually does close. But I think there's this extra acknowledgement which is not specified. I think it's like something like this. So it's not really bad, but it's not conform to the specification. So this is what they have found. Okay, so something else. This technique has also been applied in learning how the CPU cache works in a bit. So, the CPU, of course, has a little cache, and it behaves a bit like an automaton. Like depending on which cache line you pick, some things are loaded or not, and timing matters. And there is a whole industry of kind of reverse engineering how this cache works, because it's nice to analyze this in order to, for example, generate code. And they show that learning is scalable, more scalable than prior art. And I have another, so this is kind of the aim of what they do. Understanding the timing behavior of modern CPUs is crucial for optimizing code and for ensuring timing-related security and safety properties. But the timing behavior of modern high-performance processors depends on subtly and poorly documented details of the microarchitecture. So this is one of those cases where there is hardware, and you don't know exactly how it works. I mean, there's some documentation, there's some diagrams perhaps, but the exact workings are unknown. And so they use learning in order to reverse engineer what happens. And again, they use some kind of abstraction. So you see here this kind of symbolic alphabet, talking about line 0, line 1, and so on. These then converted into an intermediate alphabet, which then in the end, really translates to direct commands for the CPU. So another application, I will just do a few, right? So at Philips, they have these, they have a healthcare department where they build machines for scanners like MRI scanners and CT scanners. And they have a lot of legacy software like any other company, of course. And they want to replace it. They want to refactor the old codes, and they want to replace it by more modern code. Ideally also with less code. So what they do is they learn the old implementation, and they already have a new implementation, and they learn them both. And then you have two models, and you can compare equivalence. And so they use this to improve the new implementation. And one of the quotes is that issues were found in both the refactored and the legacy implementation. So actually both models were wrong in a sense. They did have behavior which was not wanted. And so this way they could see this. Just by looking at these state machines, they can see, well, this is a bit strange, the behavior. So this is kind of, in the diagram, this is what they did. So they have two implementations. They learn both of them. They compare equivalence. And if it's not equivalent, it could be that there is a counterexample to one of the two models. In this case, you refine the hypothesis and continue learning. If they are equivalent, you're happy, because then it means that the new version is, in terms of behavior, is the same as the old version. And that's, of course, nice. But in this case, in the state code, they actually found bugs which they had to fix anyway. So they found in inequivalent models, and they looked at the state machine and they said, well, this is actually not what we want at all. And then they fixed it. So one more protocol. So people have learned SSH. And again, in this case, it was just L* with a finite alphabet, no fancy things. And again, they did model checking afterwards, and they found various violations of the standard in 3 different implementations. Oh yeah, there's also an application in autonomous driving. How much time do I have? Okay. Yeah, again, the problem here, which is mentioned, is the model construction problem. Manual construction of formal models is expensive, error-prone, and intractable for large systems. Automating model construction would be a great enabler for us for the use of formal methods to guarantee software correctness and thereby for safety deployment of autonomous vehicles. And then they say, we demonstrate the feasibility of active automata learning algorithms for automotive industrial use. So I don't know much about this case study, it's quite recent. But you see, it's quite successful. So they have applied this to protocols, to embedded systems, to legacy code. And what you notice in many of these applications, there's a need for abstraction. Because typically the input alphabet is too big, and you have to abstract somehow in order to reduce the sizes. So either they use this by abstraction, so as I showed with the TCP, or you take a subset of inputs. And so this is a quote from an overview paper by Frits Vaandrager. By choosing a proper set of input actions and by defining an appropriate map or abstraction, we can make the small state machine visible to the learner. So even if the system is very complex and big, you can choose alphabets and observations, which then allow you to learn something small. And for the small thing, you can still do some verification. So this is also a benefit. Like even if you have a lot of code, if you're only interested in certain behavior, you choose your alphabet accordingly, and you can still try to do verification here. Because the abstraction is then somehow done automatically by the learning process. It only learns the things you care about.
Joshua, I have a question. So this part about identifying this abstraction. So clearly, if you're doing TCP, you know what you're talking about. So you know what type of abstraction you would be interested in. So to what extent can you discover these abstractions when you really don't know, like that bank card reader, what the underlying data transfer protocol is?
So my internet was a bit unstable. Can you repeat your question?
No, my question is, how do you discover abstractions, good abstractions, when you really have a complete black box that you're trying to understand? Yeah. So,
yeah, this is a very good question. I will come to this a little bit. The answer is that we don't really know exactly yet how to do this. There are some partial answers to this, and one of them will be in terms of register automata, which I will discuss. But in general, if you want to apply automata learning, there is a lot of manual work in choosing the alphabet and choosing the things you want to observe. And also, there's some other problems. So for example, for the TCP implementation, there's also timing behavior. There's some timeouts, and then things are retransmitted and so on. And in order to learn it, well, we don't have good algorithms yet for timed automata. And so they had to eliminate timing behavior. And so there's quite a lot of manual work in order to perform automata learning well. Another problem, so there was the timing problem. Another problem is when you have many components. So one of, I think from another paper, however, as it stands, learning full industrial systems, constellations of components, and even complex individual components is not within reach. So this is a bit of a scalability issue. And here's the problem you described is the manual defined abstractions. And I will come back to this a little bit. Okay, so the last part of the talk is about the advances, like the recent extensions to learning algorithms. So this is a bit of an overview. I will go into the register automata in more detail, but just to give you an idea. So there's papers on non-determinism. There's two types. So in this case, the second case, the teacher itself is non-deterministic. So sometimes it says yes, sometimes it says no. And you want to learn all the behavior. And this is quite challenging. In the first case, the teacher itself is deterministic, but the model you learn is non-deterministic. So you can make a smaller state space, in a sense. It's compressing the state space by using non-determinism. There's a paper on alternating automata. There's many papers on weighted automata, and recently also for probabilistic automata. There's papers on tree automata, learning tree automata. And these are very much related to context-free grammars, because a tree automaton is somehow, the tree structure is given, whereas in the context-free grammars, you are learning both the syntax and the tree structure. So these are somehow the same problem, but slightly different phrased. The input and output to the learner is a bit different. Yeah, so the extensions to register automata. So this is, for example, this was motivated by the TCP case study. So in principle, the TCP protocol can be described as an extended finite state machine. And these are very general types of state machines. You can, for example, say, well, we have symbols from the integers, and we read A and B and C, and we store them, and we put a guard on this last transition. For example, A cubed plus B cubed is C cubed, and you could describe a guard like this. And you could ask, for example, is Q4 reachable? So in this case, it's of course not reachable because of Fermat's last theorem. And so in this full class of extended finite state machines, many problems are undecidable. And so also learning will not really be doable. So instead of extended finite state machines, we will look at register automata. And those are like a bit in between. So they are more expressive than normal automata, but less expressive than the full class of extended finite state machines. And so what is allowed are guards where you only check for equality or inequality. Okay, so the symbols from the alphabet still come from an infinite domain, for example, the natural numbers, and we can store them and we can later compare to them. And this is kind of what happens with the sequence numbers. Like we read sequence numbers and we can compare them, but much more doesn't happen in TCP at least. So there we know that such a model could suffice, perhaps. Right, so for register automata, they are like extended finite state machines, but only with comparisons for equality. And so now, well, one thing we could do is manually define an abstraction, but we can also now try to actually automatically learn these abstractions. Automatically learn when a certain transition depends on the value or not. Now, why is this difficult? This is difficult because we cannot observe when a value is stored, and we can also not observe when a value is compared against. We can only observe the behavior it leads to. So to give an example, we have the natural numbers as our input alphabet, and there's some language, L. And suppose that the word 2 is in the language and 1 is not in the language. Then we know something. We know that the first 2, it's stored. It has to be remembered because depending on what comes after, something else happens. Right? So in this case, even if we don't observe directly that something has been stored, we know it has been stored. Right? Okay, another example. Suppose that 212 is in the language, but 211 is not. It gets more difficult because it could be that this is accepted because 2 is different from 1. Or no, maybe I should say differently. It could be that this is accepted because 2 is equal to 2, or maybe it's accepted because 1 is equal to 1. This one is rejected because 1 is equal to 1. But there's now 2 reasons for this behavior. And in order to distinguish, like in order to make the automaton and know which transition is actually used, we would have to also query what happens with 2, 1, 3. So we will ask, is this in the language? And together with these 3 words, we can decipher what happens. So this is a bit difficult, but for register automaton, this is doable. Right. But we know that we need more experiments, so we need to make more queries for these kind of automata. And this has been generating a whole line of research. So there's in fact 4 PhD theses which touch upon this topic, and including my own thesis was about this. And well, so yeah, I can say a little bit more is that what I try to do is look at symmetries for these languages, because these languages coming from register automata, they're closed on the symmetries. And if you embed these symmetries into the learning algorithm, you can learn these quite easily. There has been some recent work, which is also nice here, because, well, it's very hard to decipher exactly which guards are being used. But if you have the source code, you can at least see what kind of comparisons are being used. So what Fritz is trying to do is try to automatically combine kind of a white box verification tools like static analysis with learning. So try to see which comparisons are being made symbolically, and then have a kind of a symbolic Myhill-Nerode theorem on symbolic traces. So combining this white box and gray box verification. Let me close the window for a second. So closely related to register automata are symbolic automata. So these also deal with infinite alphabets. Oh, I'm still in the sun. Maybe like this. But the difference is that they have a richer language of predicates, but they cannot store values. And there's learning algorithms for these as well. There are also learning algorithms for languages over infinite words, so omega languages. There's extensions on timed automata, and I want to notice that, so in theory, we have some different ways of doing this, but in practice, it's still very hard because we need a way to measure time in a precise way. This is kind of what all these algorithms assume, is that we can exactly measure how long a timer takes or a certain message takes. And this, of course, in practice is never the case. So we're not close yet to actually applying these theoretical results in practice. So that's why there's so many papers, and that's why this is still kind of an open research area. There has been some generic frameworks which try to abstract away from all the details and try to give one algorithm which works in many contexts. So basically, these are using the theory of category theory in order to give a generic algorithm. And this works, for example, for weighted automata or the normal automata, also works for tree automata. And I think it also works for these register automata. Sometimes it's just a matter of finding the right category and finding the right types of functors in order to instantiate this generic algorithm to your problem, to, for example, timed automata or probabilistic automata. So there's this line of research as well, trying to give a generic algorithm. So I assume that these slides, well, you can probably watch the recording, or these slides will be online, and then you can do your own research based on these lists. Okay, to summarize, automata learning is going from observations to automata. And this enables the verification of black box systems. It's based on queries, membership queries, and equivalence queries. And we have seen many applications, and they range from bug finding to legacy software and reverse engineering. And there's also many extensions such as register automata, timed automata, and weighted automata, and so on. So I would like to thank you again. Thanks for the invitation. That's been a pleasure. Are there?
Thanks, Joshua. Perfect timing. Any questions?
So I had a question, Joshua.
Yeah, go ahead.
How does the teacher look for this omega automaton?
How does the what look for the omega link?
The teacher, like, I mean, you talked about the sampling methods for the teacher, right? So for the omega automaton, how does it look like?
I think the membership queries, they always consist of these so the omega languages. So the only words you really care about are the words of this shape. So the ultimately periodic words. So I think the memberships are in terms of these pairs. So
okay, yeah.
Okay. So maybe this is again a kind of open-ended question. So we talked about this abstraction business, but equally, I mean, in some sense, the abstraction is required to convert an infinite state object into a finite state object to learn, right? Because that's a source of, the data is a source of infinite states in some sense. So, so in general, my question is, how do you, yeah, maybe it's just the same question as before, but if you don't know that it's a kind of nice finite state object, how much can you clean it up when you're learning?
Yeah, so if you really don't know it will be a finite thing, you just start learning it, it will just not terminate. You will have to make some assumptions. So for example, you assume it's a register automaton, and then you know it's closed under symmetries. Or you know, behavior allows you to make these abstractions. There's always these kind of assumptions you have to make. You have to know something about the domain.
Yeah, so maybe what I was looking for maybe was, so are there kind of clear heuristics or some kind of guidelines as to, you know, when you're building these tables to do something which will recognize some kind of patterns which will help you?
No, I think the answer is no. In general, there's not much.
Okay.
That's a good question. I mean, that's also why his founder, he's looking into these gray box models where he wants to combine like this black box learning with like specific information from the code, like instrument code.
Okay. Yeah, that makes sense. I mean, yeah, so take some help from not, yeah, I can see that that makes sense. Yeah. Any other questions?
Yeah, to Joshua, so I'm sure you know this work better than I do, but in Tomte, wasn't there some way of learning the mapper automatically? I don't know the details there.
So exactly, so there was this algorithm for register automata which automatically learns the abstraction, and it does so by looking at the qualities like in the slides here. You look at all these kind of ways these values can compare. And then based on this, they learn automatically, they learn abstraction, and they do this with a Seeger-based approach. So they make some abstraction, and if there's a counterexample, they refine the abstraction. And it worked in some applications, but somehow it didn't always, for example, it didn't always return the minimal automaton. So they had an implementation. The theory was a bit, was not really founded well. So that was a problem with Tomte.
Okay, yeah.
And they tried to extend this also to include more interesting predicates like successors, like a +1 or +2, and then it just didn't work anymore. That's in the group of Dortmund, they had a different RA lib, and they do it in a different way, and that seemed to work a bit better. But they have stronger queries, basically. So they have queries which can talk a bit more about which predicates are being used and so on. Does this answer more or less your question?
Yes, I think so. Yeah. It's always, of course, a trade-off what you can observe and what you cannot observe. Looking at a white box system is it's a compromise, but yeah, maybe you gain something. Yeah.
And I think this is also one of the issues really for the timed automata school, because what can you exactly observe about timeout? I mean, there's so many choices here to make, and really depending on these choices, you either get an efficient algorithm or not. And that's why, well, okay, first of all, there's many work on register automata, but there's also a lot of work on these timed automata. And I think it's mostly to do with the fact what can you observe and what can you not observe. Yeah.
I see. Yeah.
Okay, any other questions or comments or anything? Okay, so then if not, let's thank Joshua again. And we have about 25 minutes before the next talk. So hope to see you back for Jako's talk. Bye-bye.